Look up at the night sky. For a moment, let yourself really see it, not just as a scattering of stars, but as an invitation, a question, a vast, beautiful mystery hanging just overhead. We live in a solar system filled with worlds we've named, mapped, and even walked upon, yet so much remains unknown. Right here, in our own cosmic backyard, lie secrets that have puzzled astronomers, defied robotic explorers, and ignited our imaginations for generations. We've sent probes to the edge of interstellar space, landed on distant moons, and trained our most powerful telescopes on planets millions of miles away. And still, the solar system holds onto its mysteries with quiet, elegant defiance. What if I told you that some of the greatest enigmas aren't light, years away in some distant galaxy, but right here within reach of our curiosity? From the haunting hexagon swirling over Saturn's North Pole to the unexplained bright spots on Ceres, from the weirdly slow spin of Mercury to the possibility of a hidden ninth planet lurking in the darkness beyond Neptune, our solar system is a place of wonder, contradiction, and breathtaking unanswered questions. Each of these puzzles isn't just a scientific riddle, it's a story, a chapter in humanity's greatest adventure, the effort to understand where we are, how we got here, and what else might be out there waiting. That's exactly what we're diving into today. This is a journey through 30 of the most compelling unsolved mysteries of our solar system, each one a reminder that discovery is far from over. We'll explore ice volcanoes that shouldn't exist, moons that hide oceans larger than Earth's, and magnetic fields that behave in ways physics can't yet explain. You're not just watching a list, you're stepping into an ongoing exploration, one that asks you to look at the familiar planets and stars with fresh eyes and a renewed sense of awe. So come with me, let's uncover the secrets hiding in plain sight just beyond our atmosphere. We begin our journey in the coldest, darkest reaches of our solar system, far beyond the orbit of Neptune, in a region teeming with icy worlds known as the Kuiper Belt. It is here that we find our first and perhaps most grand mystery, the tantalizing possibility of a hidden giant, a world so massive it could truly be called Planet 9. This isn't about reclassifying Pluto. This is a detective story written in the strange, looping paths of distant ice chunks. Astronomers poring over the orbits of small, distant objects began to notice something deeply unusual. These so-called extreme trans-Neptunian objects, some taking thousands of years to complete a single orbit, weren't scattered randomly. Instead, their elongated paths appeared to be mysteriously clustered, as if an unseen shepherd, a gravitational guide, was herding them into similar trajectories. The odds of this clustering happening purely by chance are astronomically low, leaving scientists with a compelling conclusion. The most elegant explanation is the gravitational pull of a large, undiscovered planet. This hypothetical world is no dwarf planet. Current models suggest it could be a super-Earth or a mini-Neptune with a mass up to 10 times that of our own world. Its orbit would be immensely long and elliptical, swinging from a closest approach perhaps 300 times further from the Sun than Earth is, all the way out to a staggering 800 times that distance or more. At such incredible range, it would reflect so little sunlight that it has easily escaped detection until now, a ghostly giant moving silently through the perpetual twilight of the outer solar system. The search for this elusive world is one of modern astronomy's great quests, utilizing some of the most powerful telescopes on Earth and in space, like Subaru in Hawaii, to scan the vast celestial haystack for this single, faint needle. Finding it would be a monumental discovery, fundamentally altering our maps of the solar system and forcing us to reconsider how such a large planet could have formed and been flung so far out into the frozen darkness. From the frozen, speculative darkness of the solar system's edge, we now turn our gaze inward toward the brilliant glow of the morning star. Venus shines with a deceptive beauty, but beneath its blanket of dazzling clouds lies a cautionary tale of planetary evolution gone horribly wrong. This is our second great mystery, the runaway greenhouse effect that transformed a world once potentially similar to our own into a scorching, Chinese letter hellscape. Scientists believe that in its earliest days, Venus may have been strikingly Earth-like. It formed from similar materials at a comparable distance from the Sun, and it's entirely plausible that it once possessed vast, shallow oceans of liquid water, a key ingredient for life as we know it. But somewhere along the way, the paths of these twin planets diverged catastrophically. Today, Venus is a study in extremes. Its surface temperature is a constant 860 degrees Fahrenheit, hot enough to melt lead and obliterate any chance of organic molecules surviving. The atmospheric pressure at the surface is a crushing 90 times greater than Earth's, equivalent to the pressure found nearly 3,000 feet deep in our oceans. And those beautiful reflective clouds, they aren't made of water vapor but of corrosive sulfuric acid, perpetually raining down a bitter drizzle that evaporates long before it ever hits the ground. The culprit behind this inferno is what we call a runaway greenhouse effect. It begins simply enough. A planet absorbs energy from its sun and then re-radiates it back into space as heat. An atmosphere with certain gases, like carbon dioxide, traps some of that outgoing heat, warming the planet, a necessary process that, in moderation, creates a stable climate. On Venus, however, this process spiraled out of control. The leading theory suggests that as the young sun grew brighter, Venus's closer proximity caused its oceans to begin evaporating at an increasing rate. Water vapor is itself a potent greenhouse gas, so more vapor in the air led to higher temperatures, which in turn caused even more evaporation. This created a vicious, self-reinforcing feedback loop. The point of no return was likely reached when the oceans boiled away completely, and the water vapor in the upper atmosphere was broken apart by solar radiation. The lightweight hydrogen escaped into space while the oxygen bonded with other elements. With the oceans gone, there was no way to pull the overwhelming amounts of carbon dioxide out of the atmosphere. On Earth, our carbon dioxide is locked away in oceans, rocks, and life itself through the carbon cycle. On Venus, that cycle broke down, and the gas built up to immense concentrations, now making up 96% of the atmosphere. This thick CO2 blanket traps heat with terrifying efficiency, creating the permanent furnace we see today. The profound mystery isn't just what happened, but why it happened so completely here and not on Earth. Was it simply Venus's slightly closer position to the Sun that sealed its fate? Or was there a specific catastrophic event, like a period of intense volcanic activity that pumped enough gases into the air to kick-start the runaway process? These are the questions that haunt planetary scientists, because understanding Venus's past is crucial to understanding the delicate balance that maintains our own planet's habitability. Venus stands as a stark, nearby reminder of how a world can tip from being a potential cradle of life into an uninhabitable prison, forever challenging our assumptions about what makes a planet livable. Just as Venus reminds us of the fragility of planets, Earth itself carries scars from its own violent encounters with space, and no event illustrates this danger and its enduring mystery more powerfully than the cataclysm that shook a remote corner of Siberia in the early morning of June 30th, 1908. Known as the Tunguska event, this colossal explosion remains the largest impact event in recorded human history, yet over a century later, its true cause continues to elude us. On that summer morning, eyewitnesses hundreds of kilometers away reported a brilliant blue light tearing across the sky, as bright as a second sun. This was followed by a shockwave of unimaginable force that threw people from their chairs, shattered windows, and produced a deafening roar that circled the globe twice. The epicenter was near the Podkamennaya Tunguska River in a sparsely populated region of Siberia. When scientific expeditions finally reached the site years later, led by the determined Russian mineralogist Leonid Kulik, they were met with a scene of breathtaking devastation. 80 million trees had been flattened radially over an area of 2,000 square kilometers, their trunks pointing directly away from the blast center like matchsticks scattered by a giant's hand. Astonishingly, at the very heart of this destruction, there was no crater. The trees at the center were stripped of their branches but still standing upright, scorched and bare. This bizarre pattern suggested an airburst, an explosion in the atmosphere, not an impact with the ground. The sheer energy released is almost incomprehensible. Modern estimates place the blast at between 10 and 15 megatons of TNT, nearly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. It scorched the landscape, generated seismic waves detected as far away as England, and created atmospheric shockwaves so intense that they produced glowing night skies across Europe for days, so bright that people could read newspapers outdoors at midnight. The mystery lies in what could possibly cause such a tremendous mid-air detonation without leaving any of the usual evidence behind. For decades, the leading theory pointed to a rocky body from space, most likely a stony asteroid or a fragile comet nucleus, measuring roughly 60 to 100 meters across. Traveling at tens of thousands of kilometers per hour, such an object would have encountered immense pressure as it plowed into Earth's atmosphere. The intense heat and stress would have caused it to violently disintegrate and explode several kilometers above the ground, its kinetic energy instantly converted into a fireball and blast wave. This theory neatly explains the lack of a crater and the radial forest destruction. Yet, despite numerous expeditions scouring the region, researchers have found a puzzling lack of conclusive evidence. They've recovered microscopic silicate and magnetite spheres, potential remnants of the vaporized body, embedded in the soil, but never any sizable fragments or a smoking gun like a large concentration of iridium, an element common in asteroids. The lack of definitive physical proof has, over the years, opened the door for a host of more exotic explanations. Some scientists have proposed that the object was not a stony asteroid but a small, icy comet made primarily of water, ammonia, and methane ices. A comet would explode and vaporize more completely in the atmosphere, leaving even less debris behind. Other, far more speculative ideas have included a microscopic black hole passing through the Earth, though no evidence for such an exit wound has ever been found, or even an explosive chunk of antimatter from deep space annihilating upon contact with our ordinary matter. While these fringe theories are fascinating, they are considered highly unlikely by most mainstream scientists due to the complete absence of supporting data. The true enduring power of the Tunguska mystery is its stark warning. If such an airburst were to occur today over a densely populated city, the results would be catastrophic, leveling everything for kilometers and causing untold casualties. The event underscores a very real and present threat from near-Earth objects, reminding us that our planet exists in a cosmic shooting gallery. It also represents a profound scientific puzzle, a world-altering event that we were fortunate to witness, yet one that continues to guard its secrets, challenging our understanding of planetary impacts and leaving us to wonder what truly happened in the Siberian taiga on that fateful summer morning. Leaving the haunting silence of Tunguska behind, our quest for answers brings us to the rust-colored sands of our neighboring world, Mars. Here, a far more subtle mystery unfolds, one not written in shattered trees but in fleeting, elusive whispers of gas that have the potential to rewrite our understanding of life itself. This is the enigma of Martian methane. On Earth, the presence of methane gas in our atmosphere is a straightforward sign. The vast majority of it is produced by biological processes, from the digestive systems of livestock to the decomposition of plant matter in wetlands. It's a gas of life, so when spacecraft and rovers began detecting this same gas in the thin Martian air, the scientific community was electrified. Could this be the long-sought signature of Martian microbes, past or present, quietly thriving beneath the barren surface. The first tantalizing hints came from orbital observations and Earth-based telescopes, but the most compelling data has been gathered by NASA's a Curiosity rover, which has been tirelessly sniffing the Martian air in Gale Crater since 2012. Curiosity's onboard laboratory, the tunable laser spectrometer, has recorded a fascinating and perplexing pattern. Background levels of methane are extremely low, almost negligible, but the rover has documented several sudden, dramatic spikes where methane concentrations skyrocket by a factor of 10 or more before vanishing again within a matter of hours. Even more intriguing is a clear seasonal cycle, with background levels rising predictably during the Martian summer and falling in the winter. This pattern suggests something is actively producing or releasing the gas in a way that is tied to the planet's warmer temperatures. The central mystery is the source of this gas, and it presents us with two captivating possibilities, each with profound implications. The first is geology. Methane can be created through non-biological processes, specifically a reaction between water, carbon dioxide, and certain minerals like olivine in a process called serpentinization. It could also be released from ancient methane clathrates, ice-like structures trapping the gas locked deep underground, with seasonal warming causing tiny cracks and releases. This would be a stunning discovery in its own right, pointing to a geologically active Mars with complex subsurface chemistry involving liquid water. The second possibility, of course, is biology. If the source is microbial life, it would most likely exist in isolated pockets deep underground, protected from the harsh surface radiation. These hypothetical organisms could be producing methane as a waste product, just as their counterparts, methanogens, do on Earth in oxygen-free environments like deep underground or in the guts of animals. The seasonal spike fits this idea beautifully. As the surface warms in the summer, the pressure change could force tiny amounts of this biological methane to seep up through the soil and into the atmosphere. The plot thickened considerably with the arrival of the European Space Agency's Trace gas orbiter. This sophisticated spacecraft, designed specifically to conduct a precise census of the Martian atmosphere from orbit, has so far reported a surprising result. It has detected no methane at all at the global scale. This apparent contradiction with the rover's findings is one of the most frustrating parts of the puzzle. It could mean that the methane releases are incredibly localized and short-lived, dissipating before they can spread globally, which would support the idea of very specific, isolated source points. It could also hint at a mysterious destructive process that quickly breaks the methane down in the atmosphere, something we don't yet fully understand. This is why the Martian methane mystery is so crucial and so agonizing for scientists. Each new piece of data seems to raise more questions than it answers. Determining the true source is perhaps the single most important goal for current Mars exploration, because it strikes at the heart of why we explore other worlds. Are we alone? A geological source would reveal a Mars that is more active and complex than we imagined. A biological source would be arguably the most significant discovery in human history, proving that life is not a unique phenomenon on our pale blue dot, but a more universal force. For now, the red planet holds this secret close, releasing its gaseous clues only in frustratingly brief whispers, challenging our rovers, our orbiters, and our intellects to finally solve its riddle. While the mystery of Martian methane teases us with the possibility of life, the next enigma presents a spectacle of such perfect, unnatural geometry that it seems almost manufactured. High above the cloud tops of Saturn, centered precisely on its north pole, rages one of the most stunning and inexplicable atmospheric phenomena ever witnessed in our solar system, the Great Hexagon. This is not a vague, cloud-like impression, but a near-perfect, six-sided geometric jet stream, a honeycomb pattern writ large across a world that could easily swallow our own. It is a structure so precise it looks engineered, and it has defied every conventional explanation for how weather behaves on a gas giant. The discovery of this atmospheric marvel was one of the great surprises of the Voyager missions in the early 1980s. As the twin probes flew past Saturn, their cameras captured the first glimpses of this bizarre feature, a persistent hexagonally shaped cloud pattern. But it was NASA Cassini mission which arrived at Saturn in 2004 and studied the planet for over 13 years that revealed the hexagon in all its jaw-dropping detail. Cassini's cameras showed it wasn't just a surface pattern. It was a deep-rooted, towering jet stream of air screaming along at speeds of over 300 miles per hour, with each of its 6 sides longer than the diameter of Earth. Perhaps the most astonishing fact is its longevity. This is not a temporary storm. It has been there, spinning relentlessly for at least 40 years and likely much longer, a permanent fixture in an otherwise chaotic and turbulent atmosphere. The central mystery of the hexagon is its shape. Our understanding of fluid dynamics and atmospheric physics tells us that gases and liquids on a rotating sphere like a planet naturally form circulating patterns, but they are almost always circular or oval. Think of the Great Red Spot on Jupiter, a massive hurricane that is oval, or hurricanes on Earth which are circular. These are vortices and their shape makes intuitive sense. A hexagon, with its sharp 60-degree angles and straight sides, is a form we typically associate with crystals, honeycombs, or human design, not with the swirling gases of a giant planet. It is a geometric anomaly that simply should not exist according to our standard models. Scientists have worked tirelessly to recreate the hexagon in laboratory experiments and complex computer simulations. The leading theory suggests it could be the result of a steep latitudinal gradient in the speed of Saturn's jet streams. Essentially, as different bands of atmosphere shear past each other at vastly different velocities, it might create a standing wave pattern, a stable, repeating oscillation frozen in place by the planet's rotation. On Earth, we see something similar, though far less dramatic, when a meandering river creates a stable, standing wave. In the case of Saturn's hexagon, the scale is almost unimaginable, and the wave has somehow locked into this specific 6-sided pattern. Some researchers have even drawn parallels to the polygonal shapes that can form in a spinning bucket of fluid under certain conditions in a lab. But scaling this up to the size of a planet introduces immense complications. Another layer to the puzzle is why we haven't found anything like it elsewhere. Jupiter, Uranus, and Neptune are all gas or ice giants with ferocious weather systems and rapid rotation, yet none exhibit such a stark geometric polar feature. This suggests that the conditions on Saturn are uniquely tuned to create, and more importantly, to maintain this structure. It could be related to the planet's specific internal heat flow, the depth of its atmosphere, or the unique properties of its jet streams. The hexagon's stability over decades implies it is deeply anchored, possibly extending hundreds of kilometers down into the planet's liquid metallic hydrogen interior, tapping into energy sources we cannot yet see. The enduring fascination with Saturn's hexagon lies in this clash between the seemingly artificial and the naturally occurring. It is a reminder that the universe often holds patterns far stranger than our imaginations can conjure, and that our physical laws, while robust, are still being written by the phenomena we discover. This 6-sided wonder serves as a colossal planetary scale laboratory, challenging our brightest minds to explain how such perfect geometry can emerge from and withstand the constant turmoil of a gas giant's atmosphere. A beautiful and silent reminder of how much we have yet to learn about the dynamics of the worlds around us. While Saturn's hexagon demonstrates how nature can create seemingly impossible patterns, our next mystery comes not from a planet, but from the silent, empty space between them, a single, powerful burst of radio energy that lasted for just 72 seconds, yet has captivated and confounded astronomers for decades. This is the story of the WOW signal, arguably the most famous and compelling piece of evidence in the entire search for extraterrestrial intelligence, or SETI, and an enigma that remains utterly unresolved. The event occurred on the evening of August 15, 1977, at the Big Ear radio telescope operated by Ohio State University. This was a dedicated SETI instrument silently scanning the skies night after night, hoping to find a needle in a cosmic haystack, a narrowband radio signal that could not be produced by any known natural celestial object. That night, it found one. The telescope system, which printed its data on long, continuous reams of green-lined paper, recorded a signal so strong and so perfectly matched to what theorists predicted an artificial alien transmission would look like that the volunteer researcher reviewing the data the next morning, Jerry Amon, circled the alphanumeric code indicating its incredible intensity and simply wrote, "Wow." In the margin, that exclamation of stunned discovery gave the signal its immortal name. The data itself was breathtaking in its perfection. The signal was a very narrowband transmission, focused sharply on the frequency of 1420 MHz. This is a protected frequency band. Natural cosmic objects which emit a broad spectrum of radio noise simply don't produce such a clean, focused signal. It's like hearing a pure, sustained violin note in a room full of static and chaotic noise. Furthermore, the signal's intensity rose and then fell over a 72-second period exactly as expected, matching the time it took for the Big Ear's fixed telescope to slowly drift across a fixed point in the sky due to Earth's rotation. This perfect curve confirmed the signal came from a single celestial source. Its apparent origin was in the direction of the constellation Sagittarius, near the star group Chi Sagittarii, in a region of the sky relatively poor in known stars. The immediate and most thrilling possibility was that this was the first real, verifiable greeting from another civilization, but science requires verification. The golden rule of a SETI detection is that a signal must be detected again from the same location to be confirmed, and so began the long, frustrating search for a repeat. The Big Ear telescope and later other powerful radio dishes around the world pointed again and again toward that same patch of sky. They listened for decades. They scanned that frequency and millions of others around it. They employed more sensitive equipment and more powerful computers. The result has been a profound and, for many, a deeply disappointing silence. The WOW signal was a one-off event, a cosmic flash in the pan that has never been heard again. This failure to find a repeat is the heart of the mystery and has fueled a vigorous scientific debate over its origin. If it wasn't ET, then what was it? The leading natural explanation points to a comet. In 2017, an astronomer proposed that two comets, which happened to be passing through that exact region of space at that time, could have been the source. Hydrogen clouds surrounding these comets might, in theory, emit a strong signal at the 1420 MHz frequency. However, this hypothesis has been widely critiqued and largely dismissed by many in the field. Comets are not known to emit such intense, narrowband radio bursts, and subsequent analysis showed the comets were not actually in the precise area of the signal's origin at the time. Other theories have been proposed. It could have been an intermittent natural astrophysical phenomenon we don't yet understand, perhaps a freak and never repeated burst of radio energy from a distant star or some exotic object. The most mundane and perhaps most likely explanation is that it was a signal of human origin that reflected off a piece of space debris. A secret military satellite or a piece of orbiting junk could have briefly bounced a terrestrial transmission back to Earth, creating the illusion of a celestial source. Yet, no such satellite or object has ever been definitively identified as the culprit, and the signal's characteristics were so perfectly aligned with a distant, fixed point in the sky that this explanation feels to many like an unsatisfying stretch. What makes the WOW signal endure in our collective imagination is not any single piece of data, but the powerful, tantalizing combination of them all. Its intensity was off the charts. Its narrowband frequency was the exact one scientists had predicted an advanced civilization might use. Its drift rate was textbook perfect for a celestial object. It was, in every technical sense, the perfect candidate. Its fleeting nature is what preserves its mystery. If it had been detected again, it would either be a monumental discovery or a solved puzzle. Instead, it exists in a state of quantum uncertainty, both the best evidence we have and no evidence at all. It stands as a haunting reminder of the immense challenge of searching for intelligence in a galaxy that is vast, ancient, and overwhelmingly silent. A 72-second siren song from the depths of space that we heard perfectly once and have been straining to hear again ever since. As we continue our journey outwards, we venture beyond the realm of the known planets, past even the speculative orbit of Planet 9, to the very frontier of our solar system. Here in the cold, dark expanse known as the Kuiper Belt, we encounter a mystery not of presence but of absence, a boundary so abrupt and unexplained it's as if a cosmic architect drew a line in the void and declared, "Nothing beyond this point." This is the Kuiper Belt Cliff, a sudden and dramatic drop-off in the number of icy objects that defies our fundamental understanding of how the solar system formed. The Kuiper Belt itself is a vast, donut-shaped ring of frozen remnants left over from the solar system's birth, stretching from the orbit of Neptune out to about 50 astronomical units from the Sun. Think of it as a much larger, far colder cousin to the asteroid belt. For years, astronomers predicted that this population of icy worlds would continue, gradually thinning out but still present for a significant distance further. But when we began to actually catalogue these distant objects, the data revealed something startling. Instead of a gentle, fading tail of objects, the number of Kuiper Belt objects plummets off a cliff at around 50 astronomical units. It's a stark and unexpected edge, as if someone took a cosmic broom and swept everything beyond that line clean away. This sharp boundary presents a profound challenge to the standard model of solar system formation, which is known as the NICE model. This model beautifully explains the current positions of the giant planets and the existence of the Kuiper Belt itself, suggesting that the planets migrated outward from their birth positions, scattering icy bodies into the belt we see today. However, this process should have created a Kuiper Belt that extends much further, perhaps out to 1,000 astronomical units or more, with a population that slowly diminishes with distance. The observed reality, a densely populated belt that simply stops, is a glaring anomaly that the model does not account for. It's like a puzzle where the final piece is the wrong shape, forcing us to reconsider the entire picture. So what could have sheared off the outer Kuiper Belt with such surgical precision? Scientists have proposed several compelling theories, each more fascinating than the last. The first and most dramatic idea once again invokes the gravitational hand of an unseen giant. A massive planet, perhaps the hypothetical Planet 9 itself, could have sculpted this edge. As it migrated outward early in the solar system's history, its immense gravity could have scattered and ejected the icy bodies from the outer regions, clearing out everything beyond its orbit and leaving behind the sharp cliff we observe today. Another captivating possibility looks beyond our own sun to its stellar siblings. Our sun was not born in isolation. It formed within a dense cluster of thousands of other stars. During this early period, a passing star could have ventured close enough to our infant solar system to gravitationally rip away the outer material of the proto-Kuiper Belt, stealing our distant icy bodies and leaving us with a truncated disk. This stellar thief would have long since departed, leaving no trace except for this missing population of objects. A third, and perhaps the most elegantly simple, explanation involves the conditions of the primordial solar nebula itself, the vast cloud of gas and dust from which the sun and planets formed. The leading edge of this nebula might have had a sharp drop in density, creating a natural boundary where the material was simply too sparse for sizable objects to coalesce. In this scenario, the Kuiper Belt Cliff isn't the result of a later destructive event, but a fossilized imprint of the very cloud that gave birth to our entire system, a permanent monument to the nebula's original outer limit. Each of these theories has its merits and its drawbacks, and the true answer remains one of the most active areas of research in planetary science. The Kuiper Belt Cliff is a silent witness to the violent and dynamic processes that shaped our cosmic neighborhood billions of years ago. By studying this stark boundary, we are essentially reading the final chapter of the solar system's formation story, a chapter that appears to have involved far more drama and upheaval than we ever imagined. It serves as a humbling reminder that even the farthest, coldest reaches of our own solar system still hold monumental secrets about our origins. This cosmic detective story takes us back in time over 4 billion years to the very dawn of our solar system, when the Sun was a far more timid star. Astrophysical models tell us with great certainty that our star has been steadily growing brighter over its lifetime. In its youth, the Sun was only about 70% as luminous as it is today. This presents us with one of the most enduring and fundamental puzzles in all of planetary science, the faint young sun paradox. If the early Sun was so much dimmer, the simple laws of physics dictate that Earth should have been a frozen, global snowball, its oceans locked in ice from pole to pole. And yet, the geological record shouts the opposite. We find evidence in some of Earth's oldest rocks, like the ancient stromatolites in Australia, that confirms our planet was not only unfrozen but was home to vast, warm, liquid oceans where life first emerged and thrived. This isn't just a puzzle for Earth. It extends next door to Mars, where rover missions have uncovered clear evidence of ancient riverbeds, deltas, and lakebeds, proving the red planet too had flowing water under that same faint young sun. How could both of these worlds have been so warm when their primary source of heat was so weak? The most widely accepted solution points to a dramatic difference in the very air these planets breathe. Today's Earth has a nitrogen and oxygen-rich atmosphere, but billions of years ago, it was likely a very different and much thicker cocktail of gases. The leading candidate for keeping the planet warm is a powerful greenhouse effect, far more intense than anything we experience now. Scientists propose that the ancient atmosphere may have been rich in potent greenhouse gases like methane and ammonia, or even carbon dioxide at concentrations dozens of times higher than present levels. These gases would have acted like an incredibly effective insulating blanket, trapping the little heat that did arrive from the faint sun and recycling it to maintain global temperatures well above freezing. This idea is compelling, but it runs into a problem. What was the source of these gases? On a lifeless early Earth, intense volcanic outgassing could have pumped enormous quantities of carbon dioxide into the air, creating that thick blanket. But if life arose very early, as evidence suggests, the first primitive microbes, methanogens, could have been a major source of methane, another super-potent greenhouse gas. This introduces a fascinating possibility that life itself may have played a crucial role in solving the paradox it depended on for survival. For Mars, the mystery is even more acute. The red planet, being further from the Sun, would have felt the faint Sun's weakness even more profoundly. Even a thick CO2 atmosphere might not have been enough to keep its surface above freezing for long periods. This has led scientists to propose other, more exotic solutions. Perhaps Mars had periodic, intense bouts of greenhouse warming triggered by massive volcanic eruptions or giant asteroid impacts that released enough gases and water vapor to temporarily spike temperatures and melt icy surfaces. Another theory suggests that early Mars wasn't consistently warm, but instead experienced long, deep freezes punctuated by brief, violent thaws. Alternatively, the planet's orbital dynamics, its tilt, and the shape of its path around the Sun could have been significantly different in the past. If its axis was tilted more extremely, its poles would have received more direct sunlight, potentially melting ice caps and creating the temporary rivers and lakes whose dried-up beds we see today. Some researchers have even looked back at the source of the problem itself, the Sun. Could our models of the early Sun be incomplete? What if the young Sun was more magnetically active, generating a stronger solar wind that, in turn, interacted with Earth's magnetic field to drive different chemical processes in the atmosphere? Or perhaps it emitted a different spectrum of light with more warming infrared radiation. While these stellar ideas are intriguing, the astrophysical evidence for a consistently brighter young Sun is weak, making a planetary atmosphere solution the most robust path forward. The faint young Sun paradox is far more than an academic curiosity about ancient history. It forces us to grapple with the complex, intertwined systems that make a planet habitable. It shows us that a planet's climate is a delicate dance between the light from its star, the composition of its air, the activity of its geology, and perhaps even the presence of life. Solving this puzzle for our own planet gives us a crucial template for interpreting the climate histories of the thousands of exoplanets we are now discovering around other stars. It teaches us that a star's habitable zone isn't a fixed region of space, but a dynamic concept that evolves over billions of years, shaped by the atmosphere of the world within it. The paradox stands as a testament to our planet's incredible ability to regulate its own climate and nurture life against seemingly impossible odds, a fragile balance we are only now beginning to fully appreciate. Yet for all its immense power and enduring presence, this iconic storm is not the permanent, unchanging titan we once believed it to be. Over the past century, and accelerating dramatically in recent decades, the Great Red Spot has been undergoing a profound transformation that has scientists closely watching its every move. Since the late 1800s, astronomers have been able to track its dimensions, and the data reveals a startling trend. The storm is shrinking. In the 1880s, it was wide enough to swallow nearly 4 Earths side by side. By the time the Voyager probes flew past in 1979, it was down to just over 2 Earths in diameter. Today, it measures roughly the width of a single Earth. Even more intriguing than its shrinking size is the change in its shape. What was once a robust, wide oval is becoming progressively more circular, and high-resolution images from the Hubble Space Telescope show that it is now shedding smaller, pinkish fragments from its main body, like a spinning top beginning to wobble and lose its integrity. This has led to the inevitable and somewhat melancholic question: is the Great Red Spot dying? Some computer models suggest that this shrinkage could be a natural part of the storm's long life cycle, and that it may eventually stabilize at a smaller size. Others propose a more terminal outcome, predicting that the internal dynamics that have sustained it for centuries could be fundamentally breaking down. The storm is being squeezed and constricted by opposing jet streams, powerful rivers of wind that are crashing into it from the north and south. This relentless atmospheric pressure could be slowly strangling the storm, robbing it of the energy and vorticity it needs to sustain itself. If this process continues, the unthinkable might happen. Within our lifetimes or those of our children, Jupiter's most famous feature could dissipate entirely, fading from a raging crimson maelstrom into a faint memory, leaving future astronomers to wonder at the historical accounts of a giant red eye staring out from the face of the solar system's largest planet. Whether it persists for another century or vanishes next year, the Great Red Spot story is far from over. It remains one of the solar system's most dynamic laboratories, a natural experiment in fluid dynamics on a scale we can never hope to replicate. Its longevity challenges our understanding of how energy moves through planetary atmospheres. Its color teases us with the complex chemistry of alien clouds, and its current transformation offers a front-row seat to the death of a legend. It is a humbling reminder that even the most seemingly permanent features of our cosmic neighborhood are, in the grand sweep of time, only temporary visitors, magnificent shows of nature's power that both define a world and are destined to one day fade away. Leaving behind the swirling atmospheric mysteries of Jupiter, we now turn our attention to a cosmic event of unimaginable violence that is thought to have been the very origin of our closest celestial companion. The serene, silvery moon that illuminates our night sky and guides our tides is the product of what was likely the most catastrophic event in Earth's history, and the story of its birth remains one of planetary science's most debated and fascinating chapters. For centuries, astronomers proposed a host of ideas, from the notion that the moon was a world captured by Earth's gravity to the theory that it simply formed alongside our planet from the same primordial cloud of dust and gas. But by the time Apollo astronauts brought back hundreds of pounds of lunar rocks, these older ideas had largely crumbled under the weight of new evidence. The samples revealed a shocking truth. The moon is strikingly similar to Earth in its composition, sharing many of the same isotopic fingerprints, yet it is almost completely devoid of volatile elements and water, as if it had been baked in a furnace of unimaginable heat. This confusing mix of similarities and differences gave rise to the theory that now stands as the leading explanation, the giant impact hypothesis. This scenario paints a breathtaking picture of the early solar system, a chaotic and violent time often called the Late Heavy Bombardment. Imagine a newly formed Earth, still molten and cooling, sharing its orbit with a myriad of other planetary embryos. According to the theory, a Mars-sized protoplanet, which scientists have named Theia after the mythological Greek Titan who was the mother of the moon goddess Selene, slammed into the young Earth in a glancing blow. The energy released would have been beyond comprehension, enough to melt the entire surface of our planet and vaporize a significant portion of both impacting bodies. A colossal plume of vaporized rock and metal would have been blasted into orbit around Earth, where it quickly coalesced under its own gravity, cooling to form our moon. This elegant story explains the moon's lack of a large iron core. Theia's core would have merged with Earth's, and its depletion of light, volatile elements, which would have been boiled away into space during the extreme heat of the impact. For decades, this was the clean, compelling answer. But as with all good mysteries, new data has revealed cracks in the foundation. The most significant problem lies in those isotopic fingerprints we mentioned. Advanced analysis of the Apollo samples shows that the ratios of different oxygen, titanium, and tungsten isotopes in lunar rocks are virtually identical to those found in Earth's mantle. This is a massive complication. If the moon is primarily composed of material from the impactor Theia, as the original model suggests, then its composition should be markedly different from Earth's, just as the compositions of Mars and asteroids are distinct from our own. Theia, having formed in a different part of the solar system, should have had a unique isotopic signature. The fact that Earth and the Moon are isotopic twins suggests that Theia must have been Earth's almost identical twin, a statistical improbability so vast that it challenges the entire premise. Faced with this isotopic crisis, planetary scientists have been forced to refine, reinvent, and propose alternatives to the classic model. One newer version of the giant impact suggests it was even more colossal than first thought, a high-energy, high-angular momentum impact that would have left the Earth-Moon system surrounded by a vast, searing hot cloud of mixed silicate vapor called a synestia. In this synestia model, the material from Earth and Theia would have been thoroughly churned and homogenized before the Moon condensed out of it, creating the isotopic similarity we observe. Other researchers propose a fast-spinning early Earth. If our planet was rotating once every 2 or 3 hours instead of every 24, a giant impact could have launched enough terrestrial material into orbit to form the Moon, minimizing the contribution from Theia. There are even more exotic ideas, such as the possibility that multiple smaller impacts, rather than one single giant strike, each created a debris ring around Earth that eventually coalesced into mini-moons, which later merged to form the single moon we see today. Each of these models has its own set of advantages and complications, and the debate is far from settled. The Moon's origin story is a dynamic puzzle, a reminder that even our most well-established scientific narratives must evolve when confronted with new evidence. Unraveling this mystery requires not just looking at the Moon, but understanding the chaotic and formative years of our entire solar system, a time when colossal collisions were not rare disasters but the fundamental mechanism of planetary construction. The silent, cratered face of the Moon is more than just a beautiful sight. It is a preserved record of Earth's own violent infancy, holding the secrets to how our unique planet-Moon system came to be, and by extension, how common such life-friendly arrangements might be throughout the cosmos. Leaving behind the giant planets and their atmospheric dramas, we now journey to the very heart of the asteroid belt, to a world that is far more than just a rock. The dwarf planet Ceres is the largest object in that vast ring of debris between Mars and Jupiter, and for a long time, it was little more than a fuzzy dot in our telescopes. That all changed in 2015 when NASA's Dawn spacecraft finally arrived after a long journey, its cameras slowly revealing a dark, cratered surface. But as those first images came into focus, scientists at Mission Control were met with a truly bewildering sight. There, scattered across the landscape, were incredibly bright, shining spots that stood out in stark contrast to the otherwise dark, charcoal-colored terrain. The most dazzling of these were concentrated inside a 57-mile-wide crater named Oort, appearing like a cluster of brilliant headlights switched on in the deep darkness of space. What could possibly be so reflective on this small, cold, and seemingly inert world? The immediate guesses ranged from the spectacular to the mundane. Could it be exposed water ice, gleaming metallic deposits, or something even more exotic? The mystery only deepened as Dawn used its suite of instruments to analyze the light reflecting from these spots. The data revealed the answer, and it was both definitive and surprising. The bright material wasn't ice or metal. It was a specific type of salt, primarily sodium carbonate. This is a chemical compound commonly found on Earth in places like evaporative lake beds, such as the salt pans of Death Valley. But its presence on Ceres in such vast, concentrated, and brilliantly reflective deposits was utterly puzzling. How does a world with no obvious source of liquid water end up with what looks like the residue of a dried-up, salty ocean? The leading theory is that Ceres is not the dead rock it appears to be, but a geologically active world hiding a secret beneath its crust, a vast reservoir of briny water, a subsurface ocean. This opens up the captivating possibility that Ceres is a type of world known as an ocean world, much like Jupiter's moon Europa or Saturn's moon Enceladus, though locked within the asteroid belt. The proposed mechanism for creating the bright spots is a fascinating tale of hidden plumbing and cryovolcanism. It's thought that millions of years ago, a massive impact created Oort crater, and the tremendous energy of that collision fractured Ceres' crust deep below the surface. This created a pathway for the salty, liquid water from the deep reservoir to be forced upward. Upon reaching the cold, near vacuum of the surface, this brine wouldn't erupt in a fiery volcanic explosion like on Earth, but in a far gentler, icy process. The water would instantly freeze, flash freezing into tiny ice crystals, while simultaneously boiling away into vapor in a process called sublimation. What was left behind on the crater floor was a sprawling, brilliant deposit of the salts that were dissolved in the brine, forming a dome-shaped crust that we now see reflecting sunlight with such intensity. Recent observations suggest this process wasn't a one-time event. There is evidence that briny water may have percolated up to the surface in more recent geological times, indicating that Ceres might still be weakly active today. While the salt answer solves the initial what of the bright spots, it opens up even more profound how and why questions that remain at the forefront of planetary science. The sheer volume and concentration of sodium carbonate is difficult to explain. On Earth, such deposits form through the repeated evaporation of large bodies of water over long periods under a warm sun. Ceres has no sun-driven weather system to concentrate minerals in this way. So how did this specific salt become so abundant and so pure? This suggests that the subsurface ocean on Ceres has been processing and concentrating these minerals for billions of years, perhaps through a complex cycle of freezing, thawing, and chemical separation deep within its interior. Furthermore, the energy required to drive this briny water to the surface is another puzzle. Ceres is too small to hold onto much internal heat from its formation, and it doesn't experience the intense gravitational tidal squeezing that heats the moons of Jupiter and Saturn. Some scientists point to the antifreeze properties of the salts themselves, which could lower the freezing point of the water and allow it to remain liquid at lower temperatures, or to the heat released by the radioactive decay of elements within its rocky core. The bright spots of Ceres transform this dwarf planet from a simple asteroid belt curiosity into a keystone for understanding the abundance of water and the potential for chemistry throughout our solar system. It suggests that even small, seemingly quiet worlds can harbor internal oceans and complex geological processes, expanding our definition of where to look for environments that might be suitable for life. Those shining dots of salt are more than just a pretty anomaly. They are a beacon pointing toward the hidden, dynamic nature of the smallest planets and reminding us that sometimes the greatest mysteries are not on the giant, gassy worlds, but on the small, dark ones that hold their secrets close to the vest. While the bright spots on Ceres point to mysteries within our solar system, our next puzzle involves the very fabric of space itself, as revealed by two intrepid robotic explorers on a one-way journey into the void. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were true trailblazers, the first human-made objects to travel through the asteroid belt, the first to make close-up observations of Jupiter and Saturn, and the first set on a path that would eventually take them out of the solar system entirely. For decades after their primary missions were complete, scientists continued to track their signals with exquisite precision, using the Doppler effect to measure their velocity. And that's when they noticed something deeply strange. Both spacecraft were experiencing a tiny, unexplained, and constant deceleration back towards the Sun. This minuscule but persistent tug, a drift of just 300 millionths of a meter per second squared, became known as the Pioneer anomaly. It was a deviation so small it was like measuring a single additional grain of sand slowing a truck barreling down a highway, but it was undeniable and consistent across both spacecraft. For over 2 decades, this anomaly defied all conventional explanation, creating a tantalizing possibility that our understanding of gravity itself might be incomplete. Perhaps some physicists speculated this was a sign of new physics, a hint of a modification to Einstein's theory of general relativity that would only become apparent over vast distances in the weak gravitational fields of the outer solar system. Other, more exotic theories suggested the influence of dark matter or even a previously unknown long-range force. The Pioneer anomaly became a classic scientific detective story, a ghost in the machine that refused to be ignored. The painstaking investigation to solve this mystery is a testament to scientific rigor. A dedicated team of researchers spent years recovering decades-old data from archaic formats, accounting for every conceivable force acting on the distant probes. They modeled the push from the tiny amount of heat radiating from the spacecraft's nuclear power sources, the minuscule pressure of the solar wind, and even the gravitational pull of known objects like Kuiper belt objects. For a long time, the leading candidate was thermal recoil force. The Pioneer spacecraft were designed with a main antenna always pointed directly at Earth, meaning their radioactive isotope thermoelectric generators, which produced heat and power, were positioned on long booms extending from the opposite side. The idea was that heat radiating from the body of the spacecraft could, if it bounced off the back of the large dish antenna, provide a tiny but constant pushback towards the Sun, perfectly explaining the anomaly. The true resolution, however, required a feat of historical data archaeology and modern computing power. The team managed to reconstruct the entire thermal model of the spacecraft, and their findings, published in 2012, pointed conclusively to the heat explanation. They demonstrated that the anisotropic, or uneven, radiation of heat from the spacecraft systems, primarily from the RTGs and the electrical subsystems, could indeed account for the observed deceleration. The force wasn't coming from new physics, it was coming from the spacecraft's own warmth, gently and relentlessly pushing it off its predicted course. Yet, even with this elegant solution, a small sliver of the mystery remains. The final, highly detailed thermal models came incredibly close to accounting for the entire anomaly, but not 100%. A tiny, residual signal, a whisper of a discrepancy, was still present in the data. This has led some to cautiously suggest that while thermal radiation is overwhelmingly the primary cause, there might still be room for a minuscule, additional component that our current models don't capture. The legacy of the Pioneer anomaly is therefore twofold. It stands as a magnificent example of how a precise, unexplained measurement can drive decades of investigation and lead to a deeper understanding of our own engineering, a lesson that has directly influenced the design and navigation of subsequent deep space missions like New Horizons. But it also remains a quiet, lingering reminder that our models of the universe are never truly complete, and that the most subtle of signals from the darkness can still challenge our certainty about the laws that govern the cosmos. While the Pioneer probes revealed secrets through their unexpected drift, sometimes the most telling evidence of a planet's past is written directly on its surface for all to see. Our journey now takes us to the innermost world, a place of extremes and surprises. Mercury, the solar system's smallest planet, presents a colossal contradiction. It is home to some of the largest cliff faces found anywhere. These are not ordinary geological features. They are gargantuan, staircase-like scarps that can stretch for hundreds of miles and soar over a mile high, cutting across craters and entire landscapes. They are called lobate scarps, and their existence tells a dramatic story of planetary transformation on a scale we are only beginning to understand. These immense cliffs are the unmistakable wrinkles on a shrinking world. Think of Mercury as a cosmic apple that has been left out for too long. As its interior gradually cooled over billions of years, the molten core solidified and the entire planet contracted. This process caused the crust to crumple and fracture, forcing huge sections of the surface to thrust upward and over neighboring terrain, creating these breathtaking escarpments. It's a common process for rocky planets, Earth's own crust wrinkles to form mountain ranges. But on Mercury, the scale is utterly different, far beyond what any planetary scientist predicted. The amount of shrinkage implied by the sheer number and size of these scarps is staggering. Data from NASA, a messenger mission, calculated that Mercury's radius has decreased by as much as 7 miles since its formation. To put that in perspective, a 7-mile reduction in the radius of a planet that is only about 1,500 miles across is a massive proportion, like an orange shrinking to the size of a lime. This is the heart of the mystery. Why did Mercury shrink so much more than its rocky siblings? All the terrestrial planets, Mercury, Venus, Earth, and Mars, formed hot and have been cooling down ever since. Yet, we don't see evidence of this kind of extreme global contraction on the others. The answer seems to lie in Mercury's unique and unexpected internal composition. For a long time, scientists assumed that Mercury, being so small and so close to the Sun, would have a relatively thin mantle and a proportionally small core. The Messenger mission completely upended that assumption. We now know that Mercury has a massive, enormous iron core that makes up a whopping 85% of the planet's radius. For comparison, Earth's core is only about half its radius. This left Mercury with a relatively thin outer mantle of rock, almost like a thick peel on a gigantic metal ball. This peculiar structure is the key to the extreme contraction. A planet's mantle acts as an insulating blanket, slowing down the loss of internal heat. Mercury's thin mantle provided very poor insulation for its gigantic core. With such a massive amount of metal to cool and a thin, ineffective rocky blanket to keep the heat in, Mercury's core cooled down far more rapidly and dramatically than anyone had anticipated. As this vast core cooled, it solidified and contracted with incredible force, pulling the entire planet inward and crumpling the thin crust like the skin of a drying prune. This explains the planetary scale wrinkles we see today, but this solution leads to an even deeper and more fundamental question. How did Mercury end up with such a bizarre structure in the first place? Why is it mostly a giant ball of iron with just a veneer of rock? Several compelling theories have been proposed, each involving a cataclysmic event in the planet's youth. The most dramatic is the giant impact hypothesis, a cousin to the theory that formed our moon. This scenario suggests that a colossal collision with another planetary body early in the solar system's history could have blasted away most of Mercury's original mantle and crust, leaving behind the dense, iron-rich core surrounded by a thin remnant of rocky material. The debris from this impact would have then been pulled into the sun or scattered into space. Another theory posits that the extreme heat of the young sun simply vaporized much of the outer rock layers of a larger protoplanet, leaving the dense core behind. A third idea suggests that Mercury formed from the solar nebula much closer to the sun, where the intense heat prevented lighter silicate dust from condensing as efficiently, leading to a natural accumulation of heavier iron-rich materials from the start. The story told by Mercury's giant cliffs is therefore a multi-layered mystery. The scarps themselves reveal the water planet that has shrunk immensely. The composition revealed by Messenger explains the how, a gigantic cooling core with a thin, rocky shell, but the why, the reason for that strange composition remains an active and heated debate among planetary scientists. Those magnificent, haunting cliffs are more than just geological features. They are the final chapter in a billion-year story of violent origins and dramatic change, a permanent record of the extraordinary forces that shaped the solar system's smallest and densest world. Venturing now to the cold, dark outer reaches, we encounter a pair of planetary twins whose profound differences have left scientists searching for answers. Neptune and Uranus are often grouped together as ice giants, siblings in both composition and size, born from the same frigid region of the early solar system. They are so similar that from a distance they appear as nearly identical twins, both exhibiting that beautiful, deep cerulean blue hue caused by methane in their atmospheres. Yet, when we measure the energy they emit back into space, this sibling resemblance shatters, revealing a deep and energetic mystery. Uranus, the closer of the two to the Sun, is a surprisingly quiet and thermally calm world. It radiates away into space almost exactly the same amount of energy that it receives from the distant Sun, behaving precisely as a cold, inert ball of gas should. Its twin, Neptune, is the complete opposite. Despite being even further from the Sun and receiving 40% less solar energy, it blazes with an intense internal fire, radiating more than 2.6 times the heat it absorbs. This massive energy imbalance means that Neptune generates a tremendous amount of heat from within itself, and the question of how it does this, while its seemingly identical twin does not, is one of the most perplexing puzzles of planetary science. This isn't just a mild discrepancy, it's a chasm of difference that points to a fundamental divergence in the history or internal dynamics of these two worlds. The internal heat of a giant planet is a crucial driver of its weather systems and overall appearance, and Neptune's excess energy is written plainly across its dynamic face. This is the power that fuels the fastest winds in the solar system, screaming at over 1,200 miles per hour, and drives the massive, fleeting dark storms that churn through its atmosphere, like the famous Great Dark Spot witnessed by Voyager 2. Uranus, by stark contrast, appears sluggish and nearly featureless, its atmosphere much more placid without this powerful internal engine stirring the pot. So what could possibly explain this dramatic difference between two planets that should, in theory, be so much alike? Planetary scientists have proposed several compelling theories, each delving into the cataclysmic events that might have shaped these worlds billions of years ago. The most dramatic idea involves a colossal impact, a scenario we've seen before with Earth and Mercury. The axis of Uranus is bizarrely tilted, lying almost on its side relative to the plane of the solar system. This extreme tilt is the strongest evidence that Uranus suffered a gargantuan collision with an Earth-sized object early in its history. This impact would have been so violent that it could have literally knocked the planet on its side and, crucially, scattered a huge amount of its primordial internal heat into space, leaving its deep interior effectively stillborn and thermally dead. According to this theory, Neptune either avoided such a catastrophic impact or experienced a much gentler one, allowing it to retain its original reservoir of heat from its formation. Its internal engine has been running smoothly ever since, while Uranus's was shut down in a single violent event. Another possibility looks not to a single violent event, but to the gentle, persistent processes of planetary formation and evolution. Perhaps the two planets formed at slightly different times or from slightly different compositions of the primordial solar nebula. Even a small difference in the amount of heavier rocky material mixed in with the ices could alter how the interior redistributes heat over billions of years. Neptune might have a more active interior due to a process called chemical differentiation, where heavier elements slowly sink toward the core, releasing gravitational potential energy as heat, a process that could have been stifled in Uranus by its unique internal structure or lack of convection. Then there is the simple, elegant theory of ongoing gravitational contraction. Giant planets are not formed in a single instant. They gradually accumulate mass, and as they do, they compress under their own gravity. This compression generates heat, which is then very slowly radiated away over billions of years. It's possible that Neptune is still, ever so slightly, settling and shrinking. This continual contraction would release a steady trickle of gravitational energy, manifesting as the internal heat we observe. Uranus, for reasons unknown, may have simply finished this contraction phase earlier in its history, its interior having already settled into a stable and unchanging configuration, leaving it thermally quiet. The true answer likely involves a combination of these factors, a unique recipe of formation, impact history, and internal chemistry that has left one twin blazing with inner fire and the other a quiet, cold world. Unraveling this mystery is more than an academic exercise. It speaks to the chaotic and varied processes that shaped all the planets. By understanding the divergent paths of these ice giant twins, we gain crucial insight into the formation of planetary systems everywhere, including the thousands of exoplanets we are discovering around other stars. The silent, calm face of Uranus and the dynamic, stormy visage of Neptune are a permanent reminder that even apparent twins can have dramatically different lives. Their stories written in the heat they radiate back into the cosmic dark. From the dynamic atmospheres of the ice giants, we now cast our gaze far beyond, to the most distant and theoretical frontier of our entire solar system. If you were to travel past the planets, past the Kuiper belt, and even past the Sedna like detached objects, you would eventually enter a realm of near-total darkness and profound cold. This is the proposed domain of the Oort Cloud, a vast spherical shell of icy planetesimals believed to encircle our entire solar system like a colossal, invisible cage. It is the ultimate source of the most spectacular visitors to our night sky, long-period comets, These are the comets that take thousands, even millions of years to complete a single orbit around the Sun, appearing without warning from any direction in the sky. Their existence is the primary, and indeed the only, evidence we have for this most elusive structure. The concept of the Oort Cloud is a masterpiece of scientific deduction. In the early 20th century, astronomers realized that these long-period comets couldn't possibly originate from within the known planetary system. Their highly elliptical orbits bring them screaming in from all angles, not just from the flat plane of the ecliptic where the planets reside. The Dutch astronomer Jan Oort, for whom the cloud is named, put the pieces together in 1950. He proposed that a vast, distant reservoir of icy objects must exist, a remain of the solar system's original building blocks that were scattered outward by the gravitational kicks of the giant planets during their chaotic formative years. This cloud is not a flat disk like the Kuiper belt, but a giant sphere, its inner edge beginning at around 2,000 astronomical units from the Sun. That's 2,000 times the distance from the Earth to the Sun, and stretching outward to a mind-numbing 100,000 astronomical units or even further. At such distances, the Sun is merely a particularly bright star, and its gravitational hold is so weak that the slightest nudge, a passing star, the gentle tug of the Milky Way's tide, can dislodge one of these frozen relics and send it on a multi-million-year fall into the inner solar system. The profound mystery of the Oort Cloud is that, despite being a fundamental component of our solar system model for over 70 years, we have never directly observed a single object within it. Every piece of evidence is indirect, inferred from the paths of the comets that we believe come from there. This presents an immense observational challenge. An object in the heart of the Oort Cloud is simply too far away, too dark, and too cold to emit or reflect any detectable light with our current technology. It would be like trying to spot a single, unlit charcoal briquette somewhere beyond the orbit of Pluto. Confirming its existence directly is arguably one of the most difficult tasks in all of astronomy. This leaves us in a fascinating position of scientific faith. We are virtually certain the Oort Cloud is there. The orbital dynamics of long-period comets make little sense without it. It is the only logical source for these icy wanderers, yet it remains a ghost, a prediction written in the trajectories of visitors that themselves vanish for epochs. Its confirmed existence would be the final piece in the puzzle of our solar system's architecture, the ultimate boundary of the Sun's gravitational influence. Until we can peer into that unimaginable darkness and finally glimpse one of its frozen inhabitants, the Oort Cloud will remain the solar system's grandest and most ghostly hypothesis, a testament to the power of human deduction to map the cosmos even from the faintest of clues. This dramatic shift in our understanding of Mars's climate brings us to the very heart of the mystery. What catastrophic event or series of events could have stripped away the planet's protective shield and its life-giving water? The evidence for a wet, temperate ancient Mars is now undeniable. Orbital imagery reveals the haunting scars of dried-up river valleys, vast networks of channels, and the unmistakable contours of ancient lakebeds and deltas, some of which were explored in detail by the Curiosity rover in Gale Crater. These features could only have been carved by persistent, flowing liquid water, requiring an atmosphere thick enough to keep that water from instantly boiling away in the cold vacuum and to provide the necessary pressure and warmth. So what happened to that once substantial atmosphere? The current thin, wispy Martian air is less than 1% as dense as Earth's, utterly incapable of supporting liquid water on the surface for any meaningful length of time. The story of its disappearance is a planetary tragedy written in the geology of the red planet, and scientists are piecing it together through several compelling and perhaps interconnected theories. The primary suspect has long been the relentless assault of the solar wind. Unlike Earth, Mars lacks a strong global magnetic field. our planet's molten core generates a powerful magnetic dynamo that produces a vast protective bubble, the magnetosphere, which deflects the constant stream of charged particles streaming outward from the Sun. Billions of years ago, Mars is thought to have had its own global magnetic field, but it shut down relatively early in the planet's history, perhaps as its smaller core cooled and solidified. Once that magnetic shield failed, Mars's atmosphere was left utterly exposed. NASA's MAVEN orbiter, which arrived at Mars in 2014 specifically to study atmospheric loss, provided stunning confirmation of this process. The spacecraft observed the solar wind stripping away gas from the upper atmosphere, ion by ion, a process that would have been like sandblasting a statue over eons. MAVEN data suggests this mechanism could account for a significant portion of the atmosphere's disappearance, turning a once protective blanket into a cosmic sieve. Yet, solar wind stripping may not be the whole story. Another powerful theory suggests that a great deal of the atmosphere didn't escape to space at all, but instead became locked away in the Martian rocks themselves. This process, called chemical sequestration, involves the gases reacting with surface minerals and becoming permanently trapped. On a world with surface water, a primary mechanism would be the absorption of carbon dioxide, a key greenhouse gas, into water to form carbonate rocks. On Earth, our carbon cycle recycles these carbonates back into the atmosphere through volcanism and plate tectonics. Mars, however, is a geologically stagnant world. It has no active plate tectonics to recycle its crust. Any carbonates that formed on the ancient, wet seafloors would have simply been buried and remain locked away forever. Despite extensive searching, orbiting spectrometers and rovers have found only sparse evidence of widespread carbonate deposits, which is itself a puzzling part of the mystery. If this was a major process, where are all the carbonates? Some scientists propose the water was too acidic for carbonates to form easily, or that the carbon was instead trapped in the dust and soil in different mineral forms. This leads to the most dramatic and catastrophic possibility, that a single, unimaginable impact event delivered the killing blow. The geography of Mars is heavily biased. Its northern hemisphere is a remarkably smooth, low-lying basin, averaging several kilometers lower in elevation than the rugged, cratered highlands of the south. This feature, known as the Martian crustal dichotomy, is one of the planet's most obvious characteristics from orbit. The leading explanation for this is a colossal impact very early in Mars's history, a strike so violent that it effectively scalped the entire northern half of the planet. The energy released from such an event would have been beyond comprehension, not only scarring the planet's surface but also blasting a colossal amount of its atmosphere directly into space in a single, horrifying instant. This could have been the pivotal event that pushed Mars over the edge, from a world that could hold onto its oceans to one that was irrevocably destined to become a freeze-dried desert. The truth likely involves a devastating combination of these factors. Perhaps the giant impact both stripped away a huge portion of the atmosphere and dealt a death blow to the planet's magnetic dynamo by disrupting its core dynamics. This would have left the remaining atmosphere utterly vulnerable to the solar wind, which then spent the next few billion years slowly eroding what was left, while simultaneously the planet's surface minerals were actively sucking the remaining gases into the rocks. This multi-pronged assault would have been a planetary death sentence from which there was no recovery. The water, once free-flowing on the surface, would have either frozen into the extensive subsurface ice we detect today or been broken apart by solar radiation, its hydrogen lost to space and its oxygen rusting the iron-rich surface into the global red hue that defines the planet. The story of Mars's lost atmosphere is therefore a cautionary tale of planetary fragility, a reminder that a world's habitable potential depends on a delicate and interconnected balance of a protective magnetic field, a robust atmospheric composition, and a geologically active core, a balance that Mars, for all its early promise, ultimately could not maintain. Leaving behind the grand mysteries of planetary atmospheres and lost oceans, we venture to a small, two-toned moon of Saturn that presents one of the most visually striking and geometrically perfect anomalies in the entire solar system. Iapetus is a world of stark contrasts, one hemisphere as black as charcoal and the other as bright as snow. But its most bewildering feature is a mountain range that defies all convention. Wrapping around its equator with near-perfect precision is a continuous, jagged ridge that soars up to 12 miles high and runs for over 800 miles, making it one of the tallest known mountain ranges relative to the size of the body it rests upon. From a distance, this immense ridge gives Iapetus the uncanny appearance of a cosmic walnut or a carefully stitched baseball, a shape so bizarre and unique that it exists nowhere else in all our observations of the solar system. The sheer scale and precision of this equatorial ridge present a monumental puzzle for geologists. How does a mountain range form in such a perfectly straight line along the equator of a small, frozen moon? The leading theories attempt to explain this through two radically different processes, one originating from outside the moon and the other from within. The first and most dramatic idea suggests that Iapetus once possessed its own ring system, a delicate disk of ice and rock similar to its parent planet but on a miniature scale. Over time, the moon's gravity would have pulled this ring material downward, causing it to collapse onto the surface. Because the ring would have been aligned with the moon's equatorial plane, the debris would have settled in a narrow, symmetrical band all the way around, piling up to form the massive ridge we see today. This theory elegantly explains the ridge's precise location and linear nature, but it immediately raises another difficult question. How did a small moon like Iapetus acquire rings in the first place, and where did they go afterward? The alternative explanation looks inward to the moon's own internal dynamics. This endogenic theory proposes that the ridge was forged by a dramatic upheaval from within Iapetus itself. Early in its history, the moon may have been spinning much faster than it does today, completing a rotation in just a handful of hours. This rapid spin could have generated immense forces, causing the moon's icy crust to bulge at the equator. As the moon's rotation gradually slowed due to gravitational tides, this frozen bulge might have collapsed and crumpled, thrusting upward to form the ridge. Another internal mechanism points to the freezing of a subsurface ocean. If Iapetus had a layer of liquid water hidden beneath its shell, the gradual freezing and expansion of this ocean could have exerted tremendous pressure on the crust, causing it to crack and buckle preferentially at its weakest point, the equator squeezing out a linear mountain range like toothpaste from a tube. Yet, each of these theories faces significant challenges. The ring collapse model struggles to explain why the ridge is so rugged and mountainous rather than a smooth, uniform layer of debris. The internal models, meanwhile, must account for why such intense geological activity occurred on a moon that is only 900 miles in diameter and appears to be otherwise geologically dead. Furthermore, why did this happen only on Iapetus? Other moons of a similar size and composition, like Saturn's Re, show no signs of such a feature. This uniqueness is perhaps the most baffling aspect of the mystery. It suggests that Iapetus experienced a perfect storm of conditions, a specific combination of formation history, spin rate, internal composition, and perhaps even a catastrophic encounter that was not replicated anywhere else. The silent, stark ridge stands as a permanent monument to a violent and singular event in the moon's past, an event whose true nature remains locked within the frozen rock, challenging our understanding of how even the smallest worlds can produce geological wonders on a scale that dwarfs our own planet's greatest mountain ranges. This violent reshuffling of the solar system's architecture, however, leads us to a period of cosmic chaos that left permanent scars on the worlds we've come to know. We now travel back over 4 billion years to a time when the planets were still young and the inner solar system became a shooting gallery of unimaginable violence. This is the mystery of the late heavy bombardment, a cataclysmic rain of asteroids and comets that pummeled Mercury, Venus, Earth, and Mars long after the calm of planet formation should have settled in. The most compelling evidence for this apocalyptic period is written on the face of our own moon. The lunar highlands are heavily cratered, a testament to ancient pummeling, while the darker volcanic plains, known as Maria, are significantly smoother. By radiometrically dating the Apollo samples, particularly the rocks brought back from the heavily cratered regions, scientists made a startling discovery. The ages of the melted rock that filled the largest impact basins clustered around a specific time, roughly between 4.1 and 3.8 billion years ago. This suggests that the Moon, and by extension Earth, was subjected to a sudden, intense spike in impacts hundreds of millions of years after the planets themselves had finished forming. It wasn't a gradual tailing off of debris, it was a dramatic, delayed barrage. This timing creates a profound puzzle. According to standard models of solar system formation, the vast majority of leftover planetary building blocks, the planetesimals, should have been either swept up by the growing planets or ejected into the outer solar system within the first 100 million years. The solar system should have been a much quieter place by 4 billion years ago. The fact that it suddenly became violent again implies that something massive must have destabilized a previously stable reservoir of asteroids or comets, flinging them inward toward the Sun. The leading theory that explains this delayed chaos brings us back to the movements of the giant planets and is known as the Nice model, named for the city in France where it was developed. This model proposes that Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. Initially, they orbited much closer together in a more compact configuration. Through gravitational interactions with the vast disk of leftover planetesimals beyond Neptune, the planets began a slow outward migration. The model suggests that Jupiter migrated slightly inward while the others moved outward. Eventually, Jupiter and Saturn reached a critical orbital resonance, a point where Jupiter completed 2 orbits for every one of Saturn's. This resonance created a powerful gravitational kick that suddenly destabilized the entire system. The orbits of Uranus and Neptune became wildly eccentric, and these ice giants plowed directly into the dense population of planetesimals in the primordial Kuiper belt. The consequences were catastrophic. This gravitational disturbance scattered thousands of these icy rocks, sending a hail of comets and asteroids careening into the inner solar system. The planets themselves were jostled into their current, wider orbits, while the inner worlds bore the brunt of the celestial crossfire. This event, a side effect of the planets finding their final stable orbits, provides an elegant explanation for the timing and intensity of the late heavy bombardment. It wasn't a random event, it was the direct result of the solar system's final act of architectural rearrangement. However, the Nice model is not without its own complications and challenges. Some scientists point to the geology of Earth itself, questioning whether the evidence is strong enough to support a discrete, system-wide cataclysm. They propose an alternative view called the accretion tail model, which suggests that the bombardment wasn't a sudden spike but simply the long, slow tail end of the planet formation process, with the impact rate declining smoothly over time. The clustered ages of the lunar rocks, they argue, could be a sampling bias we simply haven't found the older impact melts yet, or the massive impacts that formed the earliest basins effectively reset the lunar clock, erasing the evidence of what came before. The implications of the late heavy bombardment extend far beyond crater counting. If true, it fundamentally shaped the conditions for life on Earth. This period of extreme violence would have repeatedly sterilized the planet's surface, vaporizing any early oceans and scouring the land. Any life that may have arisen very early on would have faced an existential threat, potentially forcing it into extreme subterranean or deep sea niches to survive. In a fascinating twist, this time of destruction may also have been a time of creation. The impacting comets are thought to have delivered vast quantities of water and organic molecules to the inner planets, providing the essential ingredients for life once the bombardment finally subsided. The late heavy bombardment therefore stands as a pivotal chapter in our story, a period of terrifying chaos that may have simultaneously presented the greatest obstacle to life and delivered the very raw materials necessary for it to eventually flourish. And from the solar system's violent past, we arrive at one of its most peculiar and enduring architectural oddities, a world that seems to defy the very definition of up and down. While most planets in our solar system spin like tops with their rotational axes roughly perpendicular to the plane of their orbits, one planet has opted for a completely different approach, rolling around the Sun like a cosmic billiard ball. This is Uranus, and its extreme axial tilt of 98 degrees is one of the most bizarre and consequential features of any planet, creating a truly alien environment where conventional seasons are utterly meaningless. Imagine a world where the concept of a day or a year is completely unmoored from our earthly experience. A single orbit of Uranus around the Sun takes 84 Earth years. Due to its extreme tilt, each pole experiences 42 years of continuous, unyielding sunlight, followed by 42 years of pitch-black, deep-freeze darkness. For nearly half a century, one entire hemisphere bakes under a sun that never sets, while the other half plunges into a cold so profound and prolonged it's almost impossible to comprehend. The equator, meanwhile, experiences more familiar, rapid day-night cycles, but even these are strange, with the sun tracing a loopy, corkscrew path through the sky over the long Uranian year. This radical orientation isn't just a curious footnote. It fundamentally dictates the planet's climate, weather, and energy distribution in ways we are still struggling to understand. So how did Uranus end up in this unique and seemingly precarious position? The most dramatic and widely accepted explanation is the giant impact theory. This scenario posits that during the chaotic early days of the solar system, a protoplanet roughly 1 to 3 times the mass of Earth slammed directly into a still-forming Uranus. This wasn't a glancing blow like the impact that may have created Earth's moon. This was a catastrophic, head-on collision that literally knocked the planet sideways. The force of such an impact would have been staggering, enough to vaporize a significant portion of the impactor and Uranus's own outer layers, potentially even ejecting material that could have coalesced to form the planet's collection of moons and its faint ring system, all of which orbit in the same tilted plane. This theory is compelling because it offers a single, violent event that explains not only the extreme tilt, but also the formation of the Uranian satellites in their current alignment. However, for all its elegant simplicity, the giant impact hypothesis is not without its significant problems. The most glaring issue is one of probability. While giant impacts were certainly more common in the early solar system, a strike of this specific magnitude and directness would have been an exceptionally rare event. Furthermore, sophisticated computer simulations of such a colossal collision often result in a planet that spins far too fast or has other physical characteristics that don't match the Uranus we observe today, which rotates at a more moderate pace. This has led some planetary scientists to propose alternative, less cinematic explanations that involve gravitational dynamics rather than a single cataclysm. One such alternative suggests that Uranus's tilt developed gradually over millions of years through a complex dance of gravitational resonances. In this scenario, Uranus may have once had a massive, ancient moon far larger than any of its current satellites. The gravitational tug-of-war between this large moon, the Sun, and the other giant planets could have slowly torqued the entire Uranus system, pulling it over onto its side. Once the tilt reached a critical threshold, the system would have become locked in its new orientation. Another fascinating idea involves the migration of the giant planets. As Jupiter and Saturn moved outward in the early solar system, they may have passed through a key orbital resonance with each other, sending powerful gravitational shock waves through the entire planetary system. These waves could have destabilized Uranus's spin, causing a precession that eventually culminated in its extreme tilt, all without the need for a direct impact from another large body. The true answer may well lie in a combination of these factors: a smaller impact that gave Uranus an initial nudge, followed by gravitational interactions that finished the job over eons. Unraveling this mystery is crucial because it speaks to the very processes that shape planetary systems. Uranus's peculiar orientation is a frozen record of the incredible violence and complex gravitational negotiations that occurred billions of years ago. It serves as a permanent reminder that the planets we see today are not the pristine, orderly worlds we sometimes imagine, but the survivors of a chaotic and tumultuous construction period, each bearing the unique scars of its own dramatic birth. Yet for all the mysteries locked within distant planets and moons, perhaps the greatest enigma of all is the one that hangs in our sky every single day, the very source of light and life for our solar system. We journey now to the heart of our local universe, to a paradox that defies the most fundamental laws of physics. If you were to slowly dip a thermometer into the sun, starting from the searing surface and moving outward into the seemingly empty space above it, you would expect the temperature to drop. This is basic thermodynamics. You're moving away from the furnace, but the sun doesn't play by those rules. Its visible surface, the photosphere, is a cool 5,500 degrees Celsius. But as you rise into the wispy, ethereal outer atmosphere, the corona, the temperature doesn't fall. It skyrockets, soaring to a mind-boggling 1 to 2 million degrees Celsius. This is the solar corona heating problem, a scientific contradiction so profound that it has challenged our greatest minds for over half a century. How can the sun's atmosphere be hundreds of times hotter than its surface? It's as if the air around a flame were somehow hotter than the fire itself. For decades, this was simply a curious observation. But with the dawn of the space age and modern solar observatories, the mystery has only deepened, transforming into one of the most active and critical areas of astrophysics. The sheer violence and beauty of this superheated corona becomes terrifyingly apparent during a total solar eclipse. As the moon perfectly covers the brilliant disk of the sun, the corona is revealed as a magnificent pearly white crown of delicate, structured plasma plumes and loops stretching millions of miles into space. This isn't a calm, ethereal haze. It is the visible manifestation of the sun's tangled and immensely powerful magnetic field, a seething ocean of incandescent gas held in complex shapes by invisible forces. And it is within this magnetic architecture that scientists believe the answer to the heating mystery must lie. The central challenge is energy transport. The heat from the sun's core, generated by nuclear fusion, slowly works its way outward through radiation and the churning motion of convection zones. But this process should have deposited most of its energy at the surface, the photosphere. To heat the corona, some other mechanism must be taking over, a process that can bypass thermodynamics and carry a massive amount of energy across the apparent temperature drop and into the tenuous atmosphere above. After decades of painstaking observation and complex modeling, 3 leading theories have emerged, each championed by different groups of scientists and each with its own compelling evidence. The first and perhaps most dramatic candidate is a process called magnetic reconnection. The sun's magnetic field is not a simple bar magnet. It is a dynamic, chaotic mess of lines that are constantly being twisted, stretched, and tangled by the different rotation rates of the solar surface. Imagine tying 2 rubber bands together and then twisting them in opposite directions. They build up immense stress until snap. They break and reconfigure themselves into a new, lower energy state. In the sun's corona, this snap is magnetic reconnection. When these stressed magnetic field lines suddenly break and reconnect, they release a colossal amount of stored magnetic energy in an instant, explosively accelerating and heating the surrounding plasma. This is the process that drives massive solar flares and coronal mass ejections, events that can release more energy than a billion atomic bombs. The theory suggests that smaller, undetectable versions of these reconnection events, dubbed nanoflares, could be happening constantly across the Sun, a perpetual popcorn of tiny explosions that collectively heat the entire corona to its immense temperatures. A second major theory points its finger at powerful waves rippling through the solar plasma. Just as earthquakes send seismic waves through the Earth, the churning convection at the Sun's surface generates a constant drumbeat of waves that travel upward through the solar atmosphere. In particular, magnetocaustic waves and Alfvén waves, ripples that travel along magnetic field lines much like a wave travels along a shaken rope, are prime suspects. As these waves travel from the dense photosphere into the incredibly thin corona, their energy, which was spread out over a large volume, becomes concentrated. The waves grow in amplitude until they eventually break, like an ocean wave crashing on a shore, dumping all their vibrational energy into heat. It's a continuous, wave-driven heating system, turning the rhythmic pounding of the Sun's heart into an atmospheric furnace. The third theory combines elements of the first two, proposing that it is not the waves themselves that provide the heat, but the turbulence they create. As these various waves from the surface travel upward and interact with each other in the corona, they could create a chaotic, swirling mess of plasma, a superheated soup of eddies and currents. This turbulence would then cascade down to smaller and smaller scales, eventually dissipating its energy as heat in a process similar to how stirring a cup of coffee eventually warms it up. This theory is elegant because it doesn't rely on a single type of event, but on the constant churning motion of the entire magnetic atmosphere. So why, with powerful telescopes and advanced satellites dedicated solely to watching the Sun, do we not have a definitive answer? The problem is one of scale and detection. If nanoflares are the culprit, they are too small and too frequent for our current instruments to individually resolve against the Sun's overwhelming background brightness. If waves are the cause, tracking their energy from generation to dissipation across the vast and complex magnetic landscape of the corona is a computational nightmare. The truth, as is often the case in science, is likely a combination of all these mechanisms, with one perhaps dominating in certain regions of the corona or during different phases of the solar cycle. Unlocking this secret is far more than an academic exercise. The superheated corona is the source of the solar wind, that constant stream of charged particles that bathes the entire solar system. Understanding how it is heated is key to predicting solar storms, those violent eruptions that can disrupt satellites, endanger astronauts, and knock out power grids on Earth. The mystery of the Sun's hot crown is a beautiful million-degree puzzle that reminds us that even our closest star still holds fundamental secrets, challenging our grasp of physics and driving our quest to understand the forces that shape our very existence in space. Now we turn our attention to one of the solar system's most captivating gravitational rebels, a moon that defies all convention by moving in the completely wrong direction. This is Neptune's largest moon, Triton, and its existence is a monumental puzzle. Every other large moon in the solar system orbits its planet in the same direction as the planet's rotation, a prograde motion that speaks to a peaceful, co-formative history within a disk of gas and dust. Triton, by stark contrast, is a maverick. It orbits Neptune backwards in a retrograde direction, while also being tilted at an extreme angle relative to the planet's equator. This is the celestial equivalent of a car driving the wrong way down a cosmic freeway, and it is the single biggest clue that Triton is not a native of the Neptunian system. It is an immigrant, a captured citizen from the distant Kuiper belt that now circles a planet it was never born to know. The evidence for this capture is written not just in its orbit, but in its very composition. When Voyager 2 flew past this frozen world in 1989, it revealed a complex and active surface that looks nothing like Neptune's other, smaller moons. Triton is a geologically alive world with vast, wrinkled cantaloupe terrains, icy volcanoes that spew nitrogen gas and dark dust plumes high into its thin atmosphere, and a surface of mostly water ice with a peppering of dark organic compounds. This composition is a perfect match for other large denizens of the Kuiper belt, like Pluto. Triton is essentially a Pluto-sized world that was violently snatched from its original home in the cold outer darkness and forced into a new life as a moon of Neptune. This realization solves one mystery only to create an even more profound one. How does a planet capture such a massive object without utterly destroying it? The physics of celestial capture are brutal. An object flying past a planet on a hyperbolic trajectory has too much energy to simply be caught. It will swing around and fly right back out into space unless something can bleed off that excess energy. For a small asteroid, atmospheric drag or a series of complex gravitational nudges from other moons might do the trick, but Triton is not small. It is colossal, over 1,600 miles in diameter, and more massive than all of Neptune's other moons combined. Capturing something of this size is akin to gently lassoing a runaway freight train with a piece of string. The forces involved are almost unimaginable and should have either shattered Triton into a million pieces or catastrophically disrupted Neptune's entire satellite system in the process. Yet here it is, intact and orbiting smoothly. So how was this gravitational heist pulled off? Planetary scientists have developed two primary theories, each a breathtaking scenario of cosmic billiards. The first and most widely accepted model involves a three-body interaction. In this dramatic play, Triton was not originally alone. It was part of a binary system, two large Kuiper belt objects orbiting each other as they traveled through space. This binary pair then had a close encounter with the young Neptune. The planet's immense gravity could have torn the binary apart, capturing one member, Triton, while flinging the other away at high velocity, carrying the excess orbital energy with it. This elegant gravitational maneuver provides a neat mechanism to slow Triton down just enough to be captured into a stable, albeit initially wildly eccentric, orbit around Neptune without a direct shattering collision. The second theory is far more violent and chaotic. It suggests that Triton's capture was not a clean gravitational trick, but the messy aftermath of a giant impact within the Neptunian system itself. A massive collision between proto-moons orbiting Neptune could have generated a vast cloud of debris, temporarily creating a dense, extended atmosphere of gas and dust around the planet. As Triton flew through this extended envelope, it would have experienced tremendous aerodynamic drag, like a stone flying through thick fog, slowing it down sufficiently for Neptune's gravity to seize hold. This model accounts for the energy loss but requires a very specific and catastrophic event to have occurred at just the right moment. Whichever scenario is correct, the aftermath of the capture was just as dynamic. Triton's initial orbit would have been highly elliptical and retrograde. Over millions of years, tidal interactions with Neptune would have worked to circularize this orbit, but this process would have generated an enormous amount of internal heat within Triton through friction. This tidal heating could explain its surprisingly youthful and active surface, powering its cryovolcanoes and resurfacing its terrain long after its capture. Furthermore, this process of circularization would have had devastating consequences for Neptune's original native moon system. Triton's immense gravity would have acted like a wrecking ball, violently scattering any pre-existing regular moon. Their orbits would have been destabilized, leading to collisions and ejections, effectively wiping the slate clean. The small moons we see orbiting Neptune today are therefore likely second-generation objects, rubble that recoalesced after Triton's disruptive entrance settled down. The capture of Triton was not a gentle event. It was a transformative cataclysm that destroyed the old Neptunian system and built a new one in its place with a captured king sitting on the throne. But our journey through cosmic anomalies now brings us to a phenomenon of breathtaking beauty and deep intrigue, one that paints the face of our own moon with elegant, luminous patterns that defy all logic. These are the lunar swirls, and they rank among the most visually striking and scientifically perplexing features on any world in our solar system. Imagine a vast, abstract artist had taken a brush to the lunar surface, creating bright, swirling flourishes that can stretch for hundreds of miles. The most famous of these, Gamma, looks from orbit like a delicate cream-colored whirlpool frozen into the dark basalt plains of Oceanus Procellarum. Their appearance is utterly divorced from the moon's topography. They flow across craters, over hills, and through valleys with no change in elevation, as if they are merely a painting on the lunar canvas. This alone sets them apart from every other feature we've studied. The plot thickens when we measure the magnetic environment around these enigmatic swirls. While the moon lacks a global magnetic field like Earth's, it does possess localized, strong magnetic anomalies, and these patches of magnetism align almost perfectly with the bright swirl patterns. It appears the swirls are the surface expression of invisible magnetic bubbles shielding the lunar soil beneath. This magnetic connection provides the first major clue to the mystery. On the airless moon, the surface is constantly bombarded by the solar wind, a relentless stream of charged particles from the sun. This relentless assault has a darkening effect on the lunar soil, a process called space weathering. Over millions of years, it turns the bright, reflective regolith into a darker, redder material. Yet within the swirls, the soil remains brilliantly bright and apparently pristine. The leading theory is that the localized magnetic fields act as a miniature protective shield, deflecting the solar wind particles and preventing this darkening process from occurring, effectively preserving the bright, reflective nature of the soil underneath. This explanation, however, simply pushes the mystery one step further. If the magnetic fields are causing the bright swirls by providing protection, what created these incredibly strong and intricately shaped magnetic anomalies in the first place? The moon's small core is mostly solid and cool, incapable of generating a global magnetic dynamo now, and it's believed to have shut down billions of years ago. So what force could have magnetized the crust in these specific, swirling patterns long after the core's dynamo ceased? Scientists are investigating two primary and equally dramatic theories. The first involves a colossal impact from a comet. Unlike asteroids, which are largely rocky or metallic, comets are icy bodies with a nucleus surrounded by a vast gaseous coma, a temporary atmosphere that can be millions of miles wide. The theory proposes that if a comet's coma, dense with ionized gas, were to sweep across the lunar surface while the moon still had its global magnetic field billions of years ago, it could have created a tremendously complex and temporary magnetic environment. The interaction between the comet's magnetized coma and the moon's own magnetic field could have been imprinted onto the lunar crust, magnetizing the rocks in these intricate swirl patterns in a single, fleeting event. The pattern would then have been frozen in time, lasting long after the moon's global field disappeared and the comet itself vanished. A second, and perhaps even more fascinating, theory looks not to an impact but to a hidden subterranean structure. Some planetary scientists suggest that these magnetic swirls sit above the buried remnants of extremely ancient lava flows or other geological features rich in iron. As this material cooled very slowly in the presence of the moon's now extinct global magnetic field, the iron-rich minerals could have become permanently magnetized, recording the direction and strength of the field at that time. Later, massive impacts elsewhere on the moon could have buried these features under kilometers of ejecta, leaving their magnetic signature as the only clue to their existence. The swirling patterns might then reflect the complex shape of these buried magnetic sources. each theory has its own compelling evidence and significant challenges. The comet impact idea beautifully explains the swirling, fluid-like shapes which are difficult to generate through subsurface geology. However, it requires a very specific and relatively rare set of circumstances to have occurred. The subterranean structure model provides a more gradualistic explanation but struggles to account for the sheer scale and perfect, swirling elegance of the patterns. The truth may involve a combination of factors or perhaps a process we haven't yet considered. The lunar swirls remain a gorgeous enigma, a reminder that even our closest celestial neighbor, a world we have walked upon, still holds onto secrets written in light and magnetism, challenging us to decipher their origin. But just as we find patterns in the orbits of moons and the scars of ancient impacts, our search for order leads us to a deeper, more fundamental puzzle, one written not in rock or ice, but in the very spacing of the worlds themselves. For centuries, astronomers gazing at the solar system have been tantalized by a peculiar numerical pattern that seems to govern the arrangement of the planets, a celestial rhythm so compelling it predicted the discovery of new worlds, yet so flawed it has been relegated to a footnote in textbooks. This is the enduring enigma of the Titius-Bode law, a mathematical rule that walks the delicate line between profound insight and pure coincidence. The story begins in the 1700s with German astronomers Johann Daniel Titius and Johann Elert Bode. Titius noted a curious sequence when he assigned a number to each planet. Start with 0, then 3, and then double the number each time. So the sequence is 0, 3, 6, 12, 24, 48, and so on. Now add 4 to each number and then divide by 10. This yields a startlingly accurate prediction of the distances of the planets from the Sun in astronomical units. Mercury fits at 0.40, Venus at 0.7, Earth at 1.0, Mars at 1.6. Then there was a gap in the sequence at 2.80, followed by Jupiter at 5.2 and Saturn at 9.6. This gap at 2.8 was a glaring vacancy, and it led to a concerted search for a missing planet. That search culminated in the discovery of the first asteroid, Ceres, right in that spot, followed by thousands more, what we now know as the asteroid belt. The law's predictive power seemed nothing short of miraculous, and it was used to successfully predict the approximate orbit of Uranus before it was even found. But then came Neptune. When astronomers finally tracked down the 8th planet, its actual distance of about 30.10 was a devastating blow to the Titius-Bode rule, which predicted it should be around 38.8. The law didn't just miss, it failed spectacularly, and later, when Pluto was discovered and then demoted, its distance didn't fit the pattern either. This dramatic failure is the core of the mystery. Is the Titius-Bode law a genuine physical principle that reveals something fundamental about how planetary systems form? Or is it merely an example of apophenia, the human tendency to find patterns in random data, a numerical coincidence that we've imbued with meaning? Proponents of the law as a real phenomenon point to the mechanics of planetary formation. The early solar system was a swirling disk of gas and dust around the young sun. In such a disk, gravitational and centrifugal forces can create regions of stability and instability, potentially leading to planets forming at regular intervals. The law could be a natural outcome of the way material coalesces in these specific resonant zones within a protoplanetary disk. This idea gains some support from the fact that similar patterns in the spacing of moons have been observed around Jupiter, Saturn, and Uranus, suggesting that the underlying physics of accretion disks might produce these ratios repeatedly. Perhaps the law is a simplified, if imperfect, expression of a deeper orbital resonance principle at work during the birth of a system. The skeptics, however, offer a powerful counterargument from the field of statistics. They note that with a small sample size of only a handful of planets, it's not that difficult to find a simple mathematical formula that fits most of the data, especially one as flexible as the Titius-Bode law, which involves choosing a starting number and a multiplier. They argue that if you play with enough numbers, you can create a pattern that fits almost any set of points, and that the law's success with the asteroid belt and Uranus was a fortunate accident. The failure at Neptune, in this view, is the rule rather than the exception, finally exposing the pattern for what it always was, a charming numerical parlor trick with no real physical basis. The modern perspective leans towards a middle ground. While few scientists today believe the Titius-Bode relationship is a strict law of nature, many acknowledge that it hints at a broader truth about the tendency for planets to form in orbits that are spaced in a non-random, somewhat regular fashion due to gravitational interactions within the primordial disk. It may not be a precise predictor, but it points to the underlying architecture of stability that emerges from chaos. Its greatest legacy is perhaps not its accuracy, but its role in the history of science, a catalyst that drove the discovery of new worlds and forced astronomers to think about the solar system as an organized structure, setting the stage for our modern understanding of planetary formation and the incredible diversity of systems we are now finding around other stars. It remains a beautiful, flawed, and utterly fascinating puzzle, a testament to our eternal desire to find harmony in the heavens. Beneath the frozen, crisscrossed surface of Jupiter's moon, Europa, lies perhaps the most promising environment for life beyond Earth in our entire solar system. This isn't a mere speculation of dampness or a few subterranean pockets. This is a gargantuan, globe-spanning ocean of liquid water, containing more than twice the volume of all Earth's oceans combined, sealed under an icy shell that may be only 10 to 15 miles thick. The sheer existence of this hidden sea is a profound mystery in itself. Europa orbits more than 480 million miles from the Sun, in the deep freeze of the outer solar system, where surface temperatures plunge to -260 degrees Fahrenheit. By all rights, this world should be a solid, inert ball of ice from its core to its surface. The fact that it is not points to an incredible, dynamic source of internal power. That power is the relentless gravitational embrace of Jupiter. Europa is caught in an orbital dance with its massive parent planet and its sister moons Io and Ganymede. This dance is not perfectly circular. Europa's path is slightly elliptical, meaning its distance from Jupiter constantly changes. As it moves closer and then further away, the colossal gravity of Jupiter squeezes and stretches the moon's interior in a process known as tidal flexing. This isn't a gentle pull, it's a continuous planetary scale kneading that generates immense friction and heat deep within Europa's rocky core. This tidal heating is the primary engine that prevents the ocean from freezing solid, creating a vast, dark, liquid water environment insulated from the cold of space by the thick ice shell above it. It's a testament to the fact that a planet doesn't need to be near its star to be warm. It can cook itself from the inside out through gravitational relationships. But the mystery deepens when we consider what this heat might be fueling. On Earth, heat from the planet's core drives hydrothermal activity at the bottom of our oceans. At mid-ocean ridges, superheated water, rich in minerals, spews from vents into the cold, dark depths. These hydrothermal vents are oases of life, supporting vast, bizarre ecosystems that thrive not on sunlight but on chemical energy. The conditions within Europa's rocky seafloor are likely very similar. Scientists strongly suspect that the same tidal heating that warms the ocean is also powering hydrothermal vents on the ocean floor. If this is true, these vents could be mixing essential minerals and chemical compounds into the water, providing not only the building blocks for life, but also a potent source of energy through a process called chemosynthesis. This opens the breathtaking possibility that Europa's dark ocean could host entire ecosystems of exotic organisms, living independently of the sun, powered by the moon's internal fire and the chemistry of the deep. This leads to the final, crucial piece of the puzzle, the cycling of material. For an ocean to be habitable, it can't be a stagnant, closed system. There needs to be a way for nutrients and energy to circulate. Europa likely has a spectacularly complex chemical exchange program happening between its ocean and its icy crust. The same tidal forces that heat the interior also stress and crack the icy surface, creating the famous reddish-brown linear fractures we see. It's believed that these cracks might allow surface material, including highly oxidizing compounds created by radiation from Jupiter, to percolate down into the ocean. Conversely, material from the ocean floor, potentially rich in reducing agents from hydrothermal vents, might be carried upward through the ice. Where these two different chemical soups meet at the boundary between ice and water, they could create a potent energy gradient, a battery of sorts that could be harnessed by any potential life. This constant, slow churning could be what makes Europa's ocean a living system, connecting the energy of the core with the chemistry of the surface in a cycle that may have been ongoing for billions of years. This hidden world is a masterclass in turning a seemingly dead moon into a potential sanctuary, proving that life might find a way in the most unexpected and darkly beautiful corners of our solar system. Far from the brilliant spectacle of the sun's corona or the churning seas of a distant moon, our next mystery is a phenomenon of breathtaking subtlety, a celestial apparition so faint it is only visible from the darkest places on Earth under the most perfect conditions. For those who have witnessed it, it appears as a delicate, ethereal pyramid of soft light rising from the horizon along the path of the ecliptic just after sunset or before sunrise. This is the zodiacal light, often called the false dawn, a shimmering bridge of light that connects the planets in our night sky. For centuries, it was a beautiful curiosity, but we now know it is the visible signature of something far more intriguing. A vast, disc-shaped cloud of fine dust grains that permeates the inner solar system, stretching from the orbit of Mercury out beyond Mars. Sunlight scattering off these countless microscopic particles is what creates the gentle glow. The existence of this dust cloud is no mystery in itself. The real puzzle lies in its surprising persistence and its perplexing composition, which together defy our models of how the solar system cleans its house. The central conundrum is one of maintenance. This interplanetary dust should be a disappearing act. Once created, these tiny particles are on a doomed journey. The intense pressure of solar radiation and the solar wind constantly push them outward, a process known as pointing Robertson drag, which slowly spirals them into the sun to be vaporized. Larger grains are also vulnerable to collisions with other dust particles, grinding each other down into ever smaller fragments that are then more easily swept away. Given these relentless destructive forces, the entire zodiacal dust cloud should have been completely cleaned up within a mere 20,000 years or so, a blink of an eye on the cosmic timescale. The fact that it is still here, shining brightly after 4.5 billion years, means something must be constantly replenishing it, generating a fresh supply of dust at a rate that precisely balances this eternal loss. We are looking at a cosmic fountain, and astronomers have been searching for its source. The obvious suspects are the solar system's great litterbugs, comets, and asteroids. As these bodies travel their paths, they shed material continuously. Comets in particular are famously messy, leaving behind a trail of ice, rock, and dust their comas and tails as they are heated by the sun. When Earth passes through these old debris trails, we get meteor showers. It stands to reason that the accumulated debris from countless comets over billions of years could be the source of the zodiacal cloud. Asteroids, too, contribute through their constant collisions. When two asteroids smash together in the belt between Mars and Jupiter, they generate enormous clouds of fine dust that can then drift inward toward the sun. For a long time, the scientific consensus was that the zodiacal light was simply the blended glow of this cometary and asteroidal wreckage, the background static of our solar system's ongoing demolition derby. However, when scientists began to analyze the dust itself, both by studying its light with spectrometers and by actually collecting micrometeorites high in Earth's atmosphere. They received a stunning shock. The composition of the dust didn't match the blend they expected. While there was material from both asteroids and comets, a significant portion of the grains were rich in fluffy, porous minerals that looked far more like they came from Jupiter family comets, those originating from the Kuiper belt, than from the main asteroid belt or even the Oort Cloud comets. This was puzzling because the dynamics of dust from Jupiter family comets shouldn't allow it to migrate efficiently into the inner solar system to form the zodiacal cloud. The evidence was pointing one way, but orbital mechanics seemed to be arguing another. This discrepancy has led to the investigation of a far more dramatic and ongoing source, a massive, recent asteroid collision. The theory suggests that the current zodiacal cloud might not be the ancient, steady-state background we assumed, but could instead be the relatively fresh and expanding debris field from a single, catastrophic breakup that occurred only within the past few 100,000 years. A large asteroid collision could have injected a colossal amount of new dust into the inner system all at once, a pulse of material that we are still seeing today. This would solve the replenishment problem in one fell swoop, but it requires that such a giant, disruptive event happened surprisingly recently, and we have yet to identify the specific asteroid family that would be the smoking gun. The true answer is likely a complex mixture of all these sources, a constant drizzle of dust from myriad origins. But the zodiacal light is more than just a pretty glow or a puzzle about dirt. It is a fundamental part of our solar system's ecosystem. This dust is the raw material from which planets originally formed, and it continues to play a role today, seeding Earth's atmosphere with tons of extraterrestrial material every day. It also represents a formidable challenge for astronomers, creating a haze of scattered light that can obscure our view of faint, distant objects, a problem that future space telescopes will need to contend with. Its gentle, pervasive presence is a permanent reminder that our solar system is not a static collection of planets orbiting in empty space, but a dynamic, evolving environment filled with the ghosts of past collisions and the constant, invisible reign of creation. Orbiting just 3,700 miles above the rust-colored deserts of Mars is a small, misshapen world that seems to be literally coming apart at the seams. This is Phobos, the larger of the red planet's two moons, and its entire surface is etched with a series of bizarre, parallel grooves that form one of the most visually striking and hotly debated geological puzzles in the solar system. From a distance, these grooves look like the careful, deliberate scratchings of a cosmic claw, a set of near-perfectly straight lines that stretch for kilometers across the moon's surface, often running parallel to each other in sets. They are not random cracks, they are a systematic pattern of fracturing that covers almost the entire moon, and for decades, planetary scientists have been locked in a vigorous debate over what force could possibly have created such a uniform, widespread network of scars. The most intuitive explanation, and the one that held sway for many years, points to a colossal impact. Phobos is dominated by a massive crater named Stickney, a gaping wound that is nearly half the diameter of the moon itself. The energy from the impact that created Stickney would have been cataclysmic, easily sufficient to fracture the entire world to its core. It seems logical that these fractures would then manifest as the grooves we see on the surface. In this model, the grooves are essentially the surface expression of deep-seated fault lines, the permanent scars from a single, shattering event in the moon's distant past. The pattern could be explained by the shock waves from the impact propagating through Phobos's interior and creating zones of weakness that later expressed themselves as these parallel cracks. It's a clean, one and done answer that ties the moon's most obvious feature to its most famous wound. However, as we've studied Phobos more closely, this tidy story has begun to unravel. High-resolution images from spacecraft like NASA's Mars Reconnaissance Orbiter have revealed details that the impact fracture theory struggles to explain. For one, the grooves are not all the same age. Some appear fresh and sharply defined, while others are faded and partially filled in with dust, suggesting they were formed at different times. This is a major problem for a model that relies on a single, ancient cataclysm. Furthermore, the grooves don't all radiate directly from Stickney crater as you might expect. While many do, others seem to be aligned with the tidal axis of Phobos, the line pointing directly toward Mars. This curious alignment has led to a second, more dynamic theory, that the grooves are the result of relentless tidal stress. Phobos is caught in an inescapable gravitational dance with Mars. It orbits faster than Mars rotates, and it's also gradually spiraling inward, drawing closer to the planet by about 6 feet every century. As it does so, the tidal forces from Mars's gravity are constantly stretching and squeezing the small moon. This theory proposes that these stresses are causing the entire body of Phobos to deform, and the grooves are the surface manifestation of this ongoing process. They are essentially stretch marks created as the moon is slowly pulled apart by its parent planet's relentless grip. This elegantly explains why so many grooves align with the tidal axis and why they might form at different times as the stresses change with the moon's decaying orbit. It paints a picture of a world under constant, low-level seismic strain. Yet, even the tidal stress model has its own complications. Computer simulations of these forces often fail to produce the specific parallel patterns of grooves we observe. The stresses would likely create a more chaotic or web-like fracture network, not the remarkably organized sets of lines we see. This failure of conventional models has given rise to a third, and perhaps most dramatic, explanation, that Phobos is not a solid, cohesive body at all, but a rubble pile, a loose aggregation of boulders, rocks, and dust held together by its own meager gravity. This idea completely reframes our understanding of the grooves. If Phobos is a rubble pile, then the tidal forces from Mars are not just stretching a solid crust, they are gently shaking the entire aggregate structure. In this scenario, the grooves are not deep fractures, but rather chains of sinkholes or areas where finer-grained material is sifting down between larger boulders and draining into subsurface voids. They are the surface expression of the entire moon, slowly reorganizing itself under stress, like sand shifting in a tilted jar. This could explain the precise parallel patterns. The material would flow and settle along lines of gravitational equilibrium. It also provides a terrifying glimpse into Phobos's ultimate fate. If this process continues, rather than eventually being torn apart in a single violent event, Phobos might simply gradually disassemble itself, potentially forming a dusty ring around Mars in tens of millions of years, its grooves serving as the final testament to its slow-motion disintegration. Each of these theories, impact fractures, tidal stresses, or rubble pile reorganization, offers a compelling but incomplete narrative. The truth may lie in a combination of these forces, or perhaps in a process we haven't yet considered. The grooves of Phobos are more than just curious lines on a small moon. They are a direct window into the internal structure and dynamic history of a world that is profoundly unlike our own. They challenge our basic assumptions about what a moon is and how it behaves, forcing us to consider that some celestial bodies might be little more than fragile collections of rubble, their surfaces telling a story of constant, gentle collapse under the unforgiving pull of a giant. This remarkable flatness of our solar system, this grand celestial disk where all the planets march in near-perfect alignment, is one of its most fundamental and elegant features. It's a cosmic ballet of order, a silent testament to the processes of its birth. But if you look a little closer, you'll find a subtle yet profound kink in this perfect architecture, a slight wobble in the cosmic record that tells a more complex story. The Sun itself, the ruler of this orderly domain, is out of step. Its rotational equator is tilted by about 6 degrees relative to the orbital plane of the planets. It's as if the heart of the entire system is cocked to one side, forever glancing askance at the worlds it created. This seemingly small misalignment is a gigantic clue, a fossilized imprint from the solar system's most chaotic and formative moments, and it challenges our simplest stories of how everything came to be. The prevailing theory for this overall flatness is beautiful in its simplicity. Our solar system began over 4.5 billion years ago as a massive, slowly rotating cloud of gas and dust, a giant nebula. As this cloud collapsed under its own gravity, conservation of angular momentum caused it to spin faster and faster, much like a figure skater pulling in their arms. This rapid rotation forced the cloud to flatten into a dense, spinning disk known as the protoplanetary disk, with the infant sun blazing at its center. Within this hot, flat pancake of material, dust grains collided and stuck together, eventually growing into planetesimals, then protoplanets, and finally the planets we know today. Because they all formed from this single, flat disk, their orbits naturally settled into that same plane, a permanent record of their shared nursery. This explains the incredible flatness wonderfully, but it also predicts that the Sun, which formed from the same spinning cloud, should have its rotational axis pointed straight up out of that same plane. The fact that it doesn't mean something significant must have happened to knock it askew after the disk had already formed and the planets were beginning to take shape. So what could have exerted enough force to tilt the entire Sun? The leading hypothesis points a finger at the gravitational influence of a passing star. In the Sun's earliest days, it was not the isolated star we know today. It was born in a dense stellar nursery, surrounded by thousands of other sibling stars, all forming from the same giant molecular cloud. In this crowded cosmic neighborhood, close encounters would have been relatively common. The gravitational tug from a passing star could have exerted a torque on the outer reaches of our protoplanetary disk, or even on the young Sun itself, just enough to tilt the entire system. In this scenario, the planets, which were still coalescing from the disk, would have stayed in their original flat plane, but the Sun's axis would have been permanently shifted relative to it. This would have been an event that happened after the disk had largely formed, leaving the Sun with a lasting gravitational memory of a near miss from a stellar sibling that has long since drifted away into the galactic depths. However, not all scientists are convinced that an external stellar encounter is necessary. Another compelling theory looks inward to the complex and dynamic physics of the magnetic fields that were undoubtedly powerful within that primordial disk. The young Sun was a violently active object with a magnetic field that was both strong and intricately woven through the ionized gas of the protoplanetary disk. The theory of magnetic tilting suggests that the Sun's magnetic field could have become misaligned with its rotation axis. The powerful tug between this misaligned magnetic field and the electrically conductive disk could have created a torque, slowly pulling on the Sun and forcing its rotation axis to tilt over time. This is a more gradual, internal process, one that doesn't rely on a random and potentially rare stellar flyby, but on the fundamental magnetic personality of our own young star. A third, and perhaps most dramatic, idea once again invokes the gravitational chaos of the early solar system's architecture. We've already discussed the Grand Tack hypothesis and the NICE model, which describe how the giant planets migrated significantly from their birth positions. This planetary migration wasn't a smooth, gentle process. It was a gravitational upheaval that would have shaken the entire solar system. As Jupiter, Saturn, Uranus, and Neptune moved, their combined gravitational influence on the Sun could have been immense. The evolving, shifting balance of their gravitational pulls could have exerted a net torque on the Sun's oblate shape, slowly pushing its spin axis into its current tilted configuration. This would intimately link the Sun's misalignment to the very same violent dynamical processes that shaped the orbits of the outer planets and potentially triggered the late heavy bombardment of the inner solar system. The Sun's 6-degree tilt is therefore far more than a trivial piece of celestial trivia. It is a profound diagnostic tool, a single data point that allows us to test vastly different narratives about the solar system's infancy. Was it a quiet, isolated birth that was later jostled by a stellar neighbor? Or was it a turbulent, magnetic, and dynamically chaotic process from the very beginning, with the planets themselves playing a role in knocking their parent star off kilter? Each theory makes different predictions about how common such misalignments should be in other planetary systems. As we discover thousands of exoplanets, we are finding that such tilts are not uncommon. Many stars host planets on highly inclined or even polar orbits. This suggests that the processes that tilted our Sun, whether external stellar encounters, internal magnetic effects, or planetary migration, might be a common part of planetary system evolution. Our solar system's slight inclination is a quiet but powerful message from the past, a reminder that the serenity we see today emerged from an era of incredible violence and dynamic change. Journey now to a tiny, icy moon of Saturn that has utterly redefined our understanding of where life could exist in our solar system. This is Enceladus, a world barely 300 miles across, so small it would barely stretch from Los Angeles to San Francisco, and yet it is home to one of the most spectacular and active geological phenomena ever discovered. From its south pole, enormous geysers of water ice and water vapor blast into space at supersonic speeds, creating a magnificent plume that arcs thousands of miles above the moon's surface and feeds particles directly into one of Saturn's rings. This isn't a rare or occasional event. It's a continuous, furious eruption, a cryovolcanic display of such power and consistency that it points to a world teeming with internal energy and hidden secrets. When the Cassini spacecraft first witnessed these plumes in 2005, it was a revelation that sent shockwaves through the scientific community, transforming Enceladus from a mere speck of ice into a prime candidate in the search for extraterrestrial life. The sheer existence of these geysers is the central mystery. Enceladus is minuscule. Its gravity is so weak you could easily hit a baseball into orbit. By all conventional logic, such a small body should have lost its internal heat billions of years ago, freezing into a silent, inert ball of rock and ice. The fact that it is not only warm but violently active means something powerful and persistent is cooking it from within. The leading theory once again points to the incredible gravitational forces at play within the Saturnian system. Enceladus is locked in an orbital resonance with its larger sibling, the moon Dione. For every 2 orbits Dione completes around Saturn, Enceladus completes exactly 1. This rhythmic gravitational tug of war stretches and squeezes the small moon's interior in a process of tidal flexing, generating immense friction and heat. This is the engine that prevents Enceladus from freezing solid, but the mystery deepens when we ask how this heat is so effectively concentrated at its south pole, creating the specific conditions for these spectacular eruptions. Beneath the icy crust at that southern region lies the even more astounding secret, a global liquid water ocean. Cassini's gravity measurements confirm that this isn't a small, localized lake. It's a vast subsurface sea, enveloping the entire moon between its rocky core and its icy shell. The combination of tidal heating and the likely presence of ammonia and other antifreeze compounds dissolved in the water keeps this ocean liquid against the incredible cold of space. But the plumes are the ocean's breath, its way of communicating with the void. They erupt from a series of massive fissures nicknamed tiger stripes that slice across the south polar terrain. These are not random cracks, they are the open wounds of Enceladus, where the icy crust is believed to be at its thinnest, perhaps only a mile or 2 thick in places. The internal heat from tidal friction warms the water at the base of this ocean, causing it to rise. As this warmed water travels upward through channels in the ice, it decompresses. Some of it flashes into vapor, while the rest carries along ice particles and other materials, all forcing its way through the tiger stripe fractures and jetting out into the vacuum of space in a magnificent, continuous spray. The composition of these plumes is what makes Enceladus such a compelling target for astrobiology. Cassini didn't just photograph them, it flew directly through them, sampling their chemistry with its onboard mass spectrometers. The results were staggering. The plumes are not just simple water vapor. They are a complex cocktail containing simple organic compounds like methane and carbon dioxide, as well as more complex carbon-bearing molecules. Most tantalizing of all, the instruments detected a significant abundance of molecular hydrogen and tiny particles of silica. These two discoveries are like finding a smoking gun. On Earth, molecular hydrogen is a potent source of chemical energy for microbes that live in the deep, dark ocean near hydrothermal vents. The tiny silica particles, or nanograins, are the exact size and shape that are produced when hot water interacts with rock on the seafloor, a telltale sign of active hydrothermal vents on the ocean floor of Enceladus. This suggests that the Moon's rocky core is not inert. It is actively interacting with the ocean water through searingly hot vents, providing not just heat, but also the necessary chemical ingredients and energy gradients that could potentially power biological processes. This transforms the plumes from a geological curiosity into a direct sample of a potentially habitable environment. They act as a free, natural spacecraft, launching material from a hidden ocean we cannot yet reach into space where we can analyze it. The mechanism that creates them is a beautiful, if violent, cycle. The erupting material that doesn't escape to form Saturn's E-ring falls back to the surface as a fine, bright snow, constantly refreshing the Moon's impossibly bright, reflective surface and helping to insulate the ocean below. This ongoing process reveals a world that is dynamically balancing its internal heat with the loss of material to space, a system that may have been stable for millions of years. The enduring mystery of Enceladus is no longer just about the source of its heat, but about what might be living in that dark, warm, chemically rich ocean, fueled by the same forces that tear at its core and send its contents soaring into the blackness, a silent offering of secrets from a world that should be frozen and dead. But just as we grapple with the faint whispers of potential biology, the cosmos sometimes offers not a whisper, but a deafening, inexplicable shout. This brings us to one of the most perplexing auditory mysteries in all of astronomy, a sound so immense it seems to defy the very laws of physics themselves. It's known as the space roar, and it isn't a sound you could hear with your ears, it's a roar across the radio spectrum. A static hiss of cosmic noise that is, inexplicably, 6 times louder than anyone ever thought possible. The story of this discovery begins not with a dedicated telescope, but with a balloon. In 2006, NASA launched the Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission, or ARCADE, experiment. This wasn't a traditional orbiting observatory. It was a sophisticated radio receiver strapped to a high-altitude balloon, sent soaring above 99% of Earth's atmosphere to get a perfectly clear, undistorted listen to the universe's background radio static. The scientists' primary goal was to detect the faint radio whispers expected from the very first stars that ignited after the Big Bang. These primordial signals would be incredibly subtle, so the team had to account for every conceivable source of radio noise, from distant galaxies to the instrument's own internal heat. They meticulously subtracted the radio emissions from every known class of object and accounted for all possible interference. What they expected to be left with was near silence, a quiet canvas upon which those first stellar signals could be painted. Instead, when they filtered everything out, they were stunned to find that the background static wasn't quiet at all. It was roaring. An overwhelming, pervasive radio signal remained, and it was far, far stronger than any model had predicted. It was as if you were trying to listen for a pin drop in a silent room, only to discover the room was actually next to a jet engine. The immediate and most critical task was to rule out any local or mundane explanations. Could it be noise from our own galaxy, the Milky Way? The team's data showed the signal was isotropic, meaning it was equally loud in every direction they looked. This immediately pointed to an origin far beyond our galaxy. If it were a local phenomenon within the Milky Way, it would be concentrated along the plane of the galactic disk. Could it be from known populations of radio-emitting objects like distant quasars or starburst galaxies? Astronomers tallied up the estimated radio output from every known source in the universe and found they still fell dramatically short of accounting for this tremendous roar. Even when they added in every radio galaxy, every active supermassive black hole, and every star-forming region they could conceive of, the numbers still didn't come close. This left them with a deeply unsettling conclusion. Either there are vastly more radio sources out there than we ever imagined, and they are somehow incredibly loud yet completely invisible to our other telescopes, or our fundamental understanding of how the universe generates radio waves is profoundly incomplete. This mystery has only deepened with time, and the possible explanations venture into some of the most fascinating and speculative realms of astrophysics. One compelling line of inquiry points back to the universe's infancy. Perhaps the roar is the collective sound of the very first supermassive black holes, monsters that formed much earlier and in far greater numbers than our current models allow. Their frenzied feeding would have generated immense radio energy, and if they were common enough, their combined, redshifted signal could be creating this pervasive background static. Another theory looks to the earliest stars themselves. These population 3 stars were behemoths, hundreds of times more massive than our Sun, and they would have lived fast, died young, and exploded in hypernova of unbelievable power. The cumulative radio aftermath of countless such explosions across the early cosmos could be the source of the roar we detect today, yet other ideas are even more exotic. Some physicists have proposed that the signal could be related to dark matter, the mysterious, invisible substance that makes up most of the universe's mass. While dark matter doesn't interact with light or radio waves directly, certain theoretical particles that are candidates for dark matter, like actions, could potentially decay or annihilate and produce radio emissions as a byproduct. If this is happening, the space roar could be our first indirect detection of the dark universe announcing itself. There's even the remote, though far less likely, possibility that the roar is a signature of entirely new physics, a phenomenon we haven't yet dreamed of that challenges our core cosmological principles. The enduring power of the space roar mystery is its sheer scale and its defiance of easy categorization. It isn't a single signal from a single point like the wow signal. It is the very fabric of the universe itself, humming at a frequency we are only just beginning to perceive. It serves as a profound lesson in humility, reminding us that even when we think we have accounted for everything in our cosmic inventory, the universe always has the capacity to surprise us with a mystery that is both everywhere and nowhere, a deafening sound with no visible source, challenging us to listen more carefully and to rethink everything we thought we knew about the cosmic symphony. We've explored the faint young sun, the violent late heavy bombardment, and even the slight tilt of our own star. Each of these clues points to a dynamic and often chaotic early solar system, a far cry from the serene, orderly clockwork we sometimes imagine. But perhaps the most revolutionary idea to emerge in modern planetary science ties all these threads together into one grand, overarching narrative. The realization that the giant planets were not born in their current positions, but performed a complex and dramatic migration that completely reshaped our cosmic neighborhood. This concept, often called the grand tack or the nice model, suggests that Jupiter, Saturn, Uranus, and Neptune have all moved, and that their gravitational dance is the key to understanding almost every other mystery we've encountered. For a long time, the classic view of solar system formation was a simple one. Planets formed from a disk of gas and dust more or less where we find them today, neat and tidy. But this placid story began to unravel as we discovered exoplanet systems that looked nothing like our own, with hot Jupiters orbiting impossibly close to their stars. This forced a rethink. If giant planets could move so dramatically elsewhere, why not in our own system? The evidence for a great migration in our backyard is now overwhelming, etched into the very architecture of the solar system. The first major clue is the small size of Mars. Computer simulations of planet formation consistently show that the region just outside of Earth's orbit should have had enough material to form a much larger planet, perhaps even one the size of Earth or Venus. Instead, we have the relatively small Mars. Why is it so stunted? The leading explanation is that Jupiter acted as a gravitational barrier. The Grand TAC model proposes that Jupiter actually formed much closer to the Sun, at around 3.5 astronomical units, and then began to drift inward due to interactions with the gaseous protoplanetary disk. As it moved in, its immense gravity would have sucked up or scattered most of the planet-building material in the inner solar system, starving the region that would become Mars and leaving it to form from the scraps. But then, according to the model, Jupiter's inward journey was halted and reversed by the gravitational pull of Saturn, which was also migrating inward. The two giants became locked in a gravitational resonance, and like a pair of cosmic dancers, they reversed course and migrated back outward together to roughly their current positions. This tack maneuver, akin to a sailboat changing direction, would have left the inner solar system cleared out, explaining the petite size of Mars and the asteroid belt's sparse population. But the planetary ballet didn't end there. The outward migration of Jupiter and Saturn set the stage for an even greater upheaval in the outer solar system. This is where the nice model picks up the story. It suggests that initially Uranus and Neptune formed much closer to Saturn, and all the giant planets were nestled in a more compact configuration between about 5 and 17 astronomical units. Beyond them was a dense disk of icy planetesimals, the building blocks of the outer planets. As the giants gravitationally interacted with this disk, they began to slowly migrate. Jupiter, the most massive, moved slightly inward, while Saturn, Uranus, and Neptune drifted outward. This slow dance continued for hundreds of millions of years until Jupiter and Saturn crossed a critical orbital milestone, a 2-to-1 resonance where Jupiter completed 2 orbits for every one of Saturn's. This resonance sent a powerful gravitational shockwave through the entire system, violently destabilizing it. The orbits of Uranus and Neptune became wildly eccentric, and for a period they may have even swapped places. These ice giants plowed directly into the pristine disk of icy objects, scattering them in all directions like a gravitational cannon. A vast shower of comets and asteroids was flung inward, bombarding the inner planets in the cataclysm we now call the Late Heavy Bombardment. This event would have scarred the Moon, Mercury, and Venus, and potentially delivered both water and organic molecules to the early Earth. Eventually, after this period of chaos, the planets settled into their current, wider orbits, and the remaining scattered debris formed what we now know as the Kuiper Belt and the Oort Cloud. The evidence supporting this dramatic history is compelling. The orbital characteristics of the giant planets themselves, particularly their specific resonances and eccentricities, are best explained by a dynamic migration. The existence and specific structure of the Kuiper Belt, with its sharp outer edge and peculiar orbital groupings, are a direct fossil record of this violent scattering event. The cratering history of the Moon and the different compositions of asteroids all align with a massive disturbance that occurred long after the planets themselves had formed. Yet, for all its explanatory power, many details of the Great Migration remain hotly debated. Did the instability happen early or late? How many times did the planets cross resonances? Was Neptune's migration smooth or jumpy? The answers to these questions are crucial because this planetary dance wasn't just a spectacle of the outer solar system. It was the single most important event in shaping the potential for life on Earth. By moving Jupiter inward and then outward, it may have cleared the inner system of debris that could have resulted in a planet too massive for life to develop. By triggering the late heavy bombardment, it could have both sterilized the young Earth and then delivered the very volatiles and organics that life needed to begin. The migration of the giants is the hidden linchpin of our solar system's story, a reminder that our existence may hinge on a delicate and incredibly violent gravitational dance that happened billions of years ago, a dance whose final steps we are only now beginning to trace. And so our journey ends not with a final answer, but with a new beginning. We have ventured from the speculative darkness where a hidden giant may lurk to the scorching hellscape of a runaway greenhouse next door. We've witnessed the lingering shock of a titanic aerial blast in Siberia and puzzled over the fleeting, biological whispers in the thin Martian air. We have stood in awe before the impossible geometry of Saturn's hexagon and listened intently to the haunting, one-off cosmic siren call of the WOW signal. We have traced the abrupt edge of the Kuiper Belt's cliff, grappled with the paradox of a faint young sun that shone on a warm, wet Earth, and watched the slow, majestic fading of a giant storm that has raged for centuries. We have reconstructed the violent impact that may have given us our moon and wondered at the brilliant salt deposits shining from the dark cracks of a dwarf planet. We have chased an anomalous force slowing our farthest probes and measured the planetary scale wrinkles on a shrinking world. We have tried to understand why one ice giant burns with inner fire while its twin lies cold and still, and we have peered into the theoretical vastness of a cloud of comets so distant it has never been seen. We have revisited the cataclysmic rain that pummeled the young planets and tried to tip over an entire world to explain its bizarre sideways spin. We have probed the multi-million-degree mystery of the sun's crown and unraveled the gravitational heist that captured a rogue moon. We have marveled at the magnetic brushstrokes painting the moon with light and questioned a numerical law that both predicted and failed. We have envisioned the hidden ocean world of Europa and puzzled over the eternal, replenishing dust cloud that creates the ghostly zodiacal light. We have traced the deep grooves of a moon being slowly torn apart and sought the reason for our own sun's slight misalignment. And we have soared through the icy geysers of a tiny moon, sampling the contents of its global sea, and listened to the deafening, unexplained roar that fills the silent universe. These 30 mysteries are not a list of failures, they are a map of the future. Each unsolved riddle, each contradictory piece of data, and each inexplicable phenomenon is a beacon guiding the next generation of explorers, engineers, and dreamers. They represent the thrilling reality that our solar system, for all we have learned, remains a place of profound wonder and unanswered questions. Solving these puzzles will demand new eyes, more powerful space telescopes peering deeper into the infrared and ultraviolet, more sensitive seismometers placed on distant worlds, and more agile rovers capable of seeking out the sources of those tantalizing chemical signatures. It will require bold new missions, probes that can dive into the icy plumes of Enceladus, orbiters that can map the gravitational fields of asteroids, and perhaps one day, submarines that can navigate the dark abyss of Europa's ocean. This is the beautiful, endless work of science. It is a process of constantly rewriting the textbooks, of discovering that the universe is always stranger, more complex, and more magnificent than we had ever imagined. So we leave you with this thought: look up at the night sky tonight. You are not looking at a static museum display, but at a living, breathing, evolving cosmic neighborhood, still rich with secrets waiting to be uncovered. The greatest discoveries about our own solar system are likely still ahead of us. Now we want to hear from you. Which of these 30 mysteries captured your imagination the most? Does the possibility of Planet 9 fire up your curiosity? Or are you utterly fascinated by the hidden oceans within icy moons? Let us know in the comments below. Share your thoughts and join the conversation. And if you want to continue exploring the cosmos with us, Make sure to subscribe and hit the notification bell so you never miss a journey into the unknown. The universe